0.1 mole of the following given antiviral compound P will weigh how much in terms of 10 to the power minus 1 gram. We know that number of moles is equal to mass divided by molar mass. So, to figure out the molar mass, we need to figure out the molecular formula first. So, let us count how many carbon atoms are there. We have 4 carbon atoms here, and then 4 carbon atoms here, and then 1 carbon atom here. So, that is C9. And then hydrogen atoms, we have 1 here, 2, we have 2 here, 4, and then 1 more here, 5, 1 here, 6, and then 1 here, 7, 1 here, 8, 1 here, 9, 1 here, 10. So, H10. How many oxygen atoms are there? No, first let us count the nitrogens. How many nitrogens are there? We have 2 nitrogens. How many oxygens are there? 5 oxygen atoms. And then 1 fluorine atom and 1 iodine atom. That is the molecular formula. So, now let us find out the molar mass. 9 times 12, that will be 108, and then hydrogen 10 times 1, 10, and then nitrogen 2 times 14, 28, and then oxygen 5 times 16, that would be 80, and then fluorine 1 times 19, 19, and then iodine 1 times 127, that would be 127. So, this will be 9 plus 7 16, 16 plus 16 32. So, 2 remaining 3, 3 plus 1 4, 4 plus 2 6, 6 plus 8 14, and plus 3 17, remaining 1. So, 372. Therefore, 372 gram per mole. So, this means number of moles is given as 0.1 mole, molar mass is 372 gram per mole. So, therefore, mass is actually 37.2 gram, but the final answer we need to write it as 10 to the power minus 1 gram. So, therefore, 372 times 10 to the power minus 1 gram. So, therefore, 372 is the correct answer here, not 37.2. We have to write it as 372 times 10 to the power minus 1 gram. That would become 37.2. Here is a question based on mole concept and limiting reagent. When 81 gram of aluminum is allowed to react with 128 gram of oxygen gas, the mass of aluminum oxide produced in grams is how much? We need to find out the nearest integer. This problem involves 6 steps. First, we need to write a balanced equation. Then we need to write down the stoichiometric moles. Then we need to find the moles of aluminum as well as O2. Then we need to figure out which one is the limiting reagent. And once we find the limiting reagent, we need to equate the stoichiometric moles of limiting reagent with the stoichiometric moles of product, and then we can find the mass of Al2O3. So, let us first write the balanced equation. We have aluminum reacting with O2, and this will give Al2O3. To balance the equation, we put 3 here. Now we have 6 oxygen atoms. So, that means we need to put 2 here. Now we have 4 aluminum atoms. Therefore, we need to put 4 here. Now the equation is balanced. Stoichiometric moles is, we write this way, number of moles of aluminum divided by the stoichiometric coefficient. Whatever is the coefficient we have, that we bring it down. And number of moles of O2 divided by 3, and number of moles of Al2O3 divided by 2. Now, let us find the number of moles of aluminum and O2 based on the weight given. We know that number of moles is equal to mass divided by molar mass. Therefore, number of moles of aluminum is equal to mass given is 81 gram Molar mass of aluminum is given as 27 gram per mole, and therefore this will be 3 moles. How about O2? Number of moles of O2 is equal to mass given is 128 gram. Molar mass of O2 is 32 gram per mole. Here they have given the atomic mass of oxygen. Therefore, for O2 you have to multiply by 2 because we have 2 oxygen atoms. Therefore, this is 32 gram per mole. Therefore, this will be 4 moles. Let us find out the limiting reagent. Limiting reagent is equal to number of moles of reactant, let us keep it as X, divided by the stoichiometric coefficient of X, and whichever is the smallest out of this. The smallest out of this is the limiting reagent. Therefore, number of moles of aluminum, we found it as 3 moles, isn't it? So, therefore, 3 mole divided by stoichiometric coefficient is 4. Therefore, this is equal to 0.75 mole. Number of moles of O2, we found it as 4 moles. Therefore, 4 moles and the stoichiometric coefficient was 3. Therefore, this will be 1.33 moles, which is smaller, this is smallest. Therefore, aluminum is the limiting reagent in this case. Therefore, number of moles of aluminum divided by 4 should be equated with the number of moles of Al2O3 divided by 2. This is the equation that we should use because our limiting reagent is aluminum. Therefore, we can equate it. Now, let us find the mass of Al2O3. Therefore, number of moles of Al2O3 is equal to 2 times 3 mole divided by 4. So, number of moles of Al2O3 will be equal to 3 by 2 moles. Therefore, mass of Al2O3 is equal to number of moles of Al2O3 times molar mass of Al2O3. Molar mass of Al2O3 is, we have 2 aluminum atoms, therefore 2 times 27, that is equal to 54. We have 3 oxygen atoms, therefore 3 times 16, that is equal to 48. Therefore, this total will be 102 gram per mole. Therefore, this is equal to 3 by 2 moles times 102 gram per mole. This will become 51. 51 times 3 is 153 gram. So, that is the mass of Al2O3. Therefore, the correct answer here is 153. 2.8 times 10 to the power minus 3 moles of CO2 is left after removing 10 to the power 21 molecules from its X milligram sample. The mass of CO2 taken initially is how much? We know that number of moles is equal to mass divided by molar mass. We need to figure out the mass of CO2 that is taken initially here, which we can also equate that with the number of molecules divided by Avogadro number. So, these are the two equations that we are going to use here. Number of moles that are initially available is equal to mass divided by molar mass. Mass is X milligram. Molar mass of CO2 is 44 gram per mole because we have 1 carbon and 2 oxygen, and therefore, this we can write it as X times 10 to the power minus 3 gram divided by 44 gram per mole. So, this will be simply X times 10 to the power minus 3 divided by 44 mole. Now, what is the number of moles removed? We have removed 10 to the power 21 molecules. In 1 mole, we have Avogadro number of molecules. Therefore, let us use this equation now. So, 10 to the power 21 molecules divided by 6.02 times 10 to the power 23 molecules per mole. And let us write this one as 10 times 10 to the power 20, so that we can use 10 to the power minus 3 as the common factor, divided by 6.02 times 10 to the power 23 mole. So therefore the number of moles removed will be 10 divided by 6.02 times 10 to the power minus 3 mole. Now number of moles left is equal to number of moles that are initially available minus number of moles that are removed, and therefore number of moles left is 2.8 times 10 to the power minus 3 mole. Initially available is x times 10 to the power minus 3 divided by 44 minus number of moles removed is 10 divided by 6.02 times 10 to the power minus 3. Let us take out the 10 to the power minus 3, that is common. So therefore x divided by 44 minus 10 by 6.02, we can write it as 1.66, and we have 10 to the power minus 3 on this side also, we can cancel that. So if we bring the minus 1.66 on the other side, it would become plus. So 2.8 plus 1.66, and that will be 4.46 times 44 equal to x. So 40 times 4, 160, 4 times 4, 16. If we take the 0.46 as 0.5, then it will be 22. So this will be approximately 198 milligrams. The answer should be approximately that. So therefore option 1 is correct. Keep it in mind that the sample is in milligrams. We converted into grams. So therefore the unit of the sample is milligrams. 0.01 mole of an organic compound X containing 10% hydrogen on complete combustion produced 0.9 gram water. What is the molar mass of X in gram per mole? We have an organic compound X that contains 10% hydrogen undergoing combustion, and it gives water whose weight is given as 0.9 gram. Number of moles of X is equal to mass of X divided by molar mass of X. Molar mass of X, we need to figure it out. Here the mass of X is given in an indirect way. So mass of X is equal to 0.01 mole times molar mass of X. Now what is the mass of hydrogen in X? 10%. Whatever is the total mass of X, in that 10% is hydrogen. Therefore this is equal to 0.01 mole times molar mass of X times 10 by 100, because it is mentioned as 10%. Let us keep it this way. What is the number of moles of hydrogen in X? Number of moles of hydrogen in X will be mass of hydrogen in X divided by molar mass of hydrogen. Molar mass of hydrogen is 1 gram per mole. Therefore this entire thing divided by 1 gram per mole. So we need to figure out now the number of moles of hydrogen, and that is also mentioned in an indirect manner through water. Number of moles of water, let us figure it out first. Number of moles of water is equal to 0.9 gram divided by molar mass of water is 18 gram per mole. Therefore this will be 0.05 mole. However, number of moles of hydrogen is equal to 2 times the number of moles of water. Why? Because atomicity of water is 3. We have 2 hydrogen atoms and 1 oxygen atom. Therefore number of moles of hydrogen we need to multiply with 2. Therefore 2 times 0.05 moles. So that means number of moles of hydrogen is equal to 0.1 mole. Therefore 0.1 mole is equal to 0.01 mole times molar mass of X times 10 by 100 times 1 gram per mole. So this 10.01, that will become 0.1 mole. So we can cancel that. So this means molar mass of X is equal to 100 gram per mole. That's the correct answer. Therefore, the correct answer here is 100. Consider the reaction given below. If 174 gram of butane reacts with 320 gram of O2, find the volume of water formed in milliliter. Density of water is given as 1 gram per milliliter. We know that density is equal to mass by volume. We need to find the volume. Density is given. So that means we need to figure out the mass. Let us first check whether the reaction is self-balanced or not. On the reactant side, we see 4 carbons. On the product side too, we see 4 carbons. On the reactant side, we see 10 hydrogens. On the product side too, we see 10 hydrogens because 5 times 2, 10. And then on the reactant side, we see 13 oxygen atoms because 13 by 2 times 2, so it would be 13. On the product side too, we see 8 plus 5, 13. So therefore, the reaction is already self-balanced. Now let us write the stoichiometric moles. How do we write stoichiometric moles? Number of moles of butane divided by 1. Whatever is the stoichiometric coefficient, we just bring it down. And then number of moles of O2 divided by 13 by 2. And then number of moles of CO2 divided by 4 and number of moles of water divided by 5. Now, depending upon which one is the limiting reagent, whether butane is the limiting reagent or O2 is the limiting reagent, that we need to figure out. And then depending upon that, we have to compare the stoichiometric moles with the stoichiometric moles of water so that we can find out the answer. Now, let us find the number of moles of butane and number of moles of O2. Number of moles of butane is equal to mass divided by molar mass. So, 174 gram, that is the given value here. And the molar mass of butane is 4 times 12, that is 48, and 10 times 1. So, 58 gram per mole. So, therefore, this is 58 gram per mole. So, this means this will be 3 moles. Number of moles of butane is 3 moles. How about number of moles of O2? Number of moles of O2 will be 320 gram, that is the given weight, divided by molar mass of O2 is 32 gram per mole because 2 oxygen atoms. So, 16 times 2, so 32. Therefore, this will be 10. Now, which one will be the limiting reagent? Limiting reagent is number of moles of reactant divided by stoichiometric coefficient of reactant, and whichever is smallest out of that is the limiting reagent. So, for butane, what is the number of moles we found? It was 3 moles. Stoichiometric coefficient is 1. So, therefore, 3 by 1 is 3. How about O2? For O2, we found that 10 moles. Stoichiometric coefficient is 13 by 2. So, therefore, when the 2 goes up, it would be 20 by 13. So, obviously, 3 is greater than 20 by 13 because this will be somewhere around 1.5 something. So, therefore, which one will be the limiting reagent? The O2 is the limiting reagent here. So, therefore, what we need to compare? We need to compare the stoichiometric moles of O2 with the stoichiometric moles of water. So, therefore, 2 times number of moles of O2 divided by 13, I just brought the 2 up, equal to number of moles of H2O divided by 5. So, therefore, number of moles of H2O is equal to 10 times number of moles of O2 divided by 13. Number of moles of O2 we found was 10 moles. So, therefore, 10 times 10, therefore, 100 by 13. Now, we need to figure out 100 by 13. So, let us do that.
So 7 times will be 91. 7 times 13 is 91. Remaining 9 we can't divide, so put a 0. And then 6 times 13 is 78. Remaining 12 we can't divide, so put a 0 once again. And then if we do 9 times 13, then it would be 117. So remaining 3. So we will just keep it to 2 digits, 7.69. So therefore, number of moles of H2O is equal to 7.69 moles. So therefore, mass of H2O is equal to, molar mass of H2O is 18 gram per mole. So 18 gram per mole times number of moles of H2O, that is 7.69. Therefore, mass of H2O 769 times 18. 9 times 8 is 72. So 2 remaining 7. 8 times 6, that would be 48. 48 plus 7, so 55. 5 remaining 5. And then 8 times 7, that would be 56 plus 5, so 61. And then 9, 6, 7. Therefore 2, 9 plus 5, 14, 4 remaining 1. So 7 plus 1 plus 1, so 8. And then 7 plus 6, 13. Therefore 138.42 gram. That's the mass of H2O. Now volume is equal to mass divided by density. So therefore 138.42 gram divided by density is given as 1 gram per milliliter. So therefore gram we can cancel. So it would be 138.42 milliliter volume is. So if we want the nearest number, then volume is equal to approximately 138 milliliter. That's the correct answer.
When 0.01 mole of an organic compound containing 60% carbon was burned completely, 4.4 gram of CO2 was produced. In that case, what is the molar mass of the compound in gram per mole? Let's say we have an organic compound X that contains 60% carbon undergoing combustion, and it is giving CO2 whose weight is given as 4.4 gram. So this means number of moles of CO2 is equal to mass divided by molar mass. Molar mass of CO2 is 44 gram per mole, because 12 plus 32, we have 2 oxygen atoms. Mass of CO2 is given as 4.4 gram. Therefore 4.4 divided by 44 gram per mole. So this means this is 0.1 mole, number of moles of CO2. Atomicity of CO2 is 3, but we have only one carbon atom. This means number of moles of CO2 is equal to number of moles of carbon. Now, number of moles of X is equal to mass of X divided by molar mass of X. The mass of X here is given in an indirect manner. They mentioned it as 60% carbon. Therefore, mass of carbon in X is equal to number of moles of X times molar mass of X times 60 by 100, because whatever is the total mass of X, in that 60% is carbon. Therefore 60 by 100. Now let's keep it as equation 1. Number of moles of carbon in X is equal to mass of carbon in X divided by molar mass of carbon. Mass of carbon in X, we can substitute this. Molar mass of carbon is 12 gram per mole. Therefore, number of moles of carbon in X is equal to 0.01 mole times molar mass of X times 60 divided by 12 gram per mole, that is the molar mass of carbon, times 100. 1010 we can cancel here. 6, 2 times 6 is 12, therefore 2 here. And number of moles of carbon in X, we already figured it out, that is 0.1 mole. Therefore 0.1 mole is equal to 0.01 mole times molar mass of X divided by 20 gram per mole. Therefore, molar mass of X is equal to, if we cross multiply, then it will be 2 gram per mole divided by 1 into 10 to the power minus 2. Therefore, when this comes up, it will become 200 because 2 times 100. So, 200 gram per mole. So, molar mass of X is equal to 200 gram per mole. 200 is the correct answer here. If the uncertainty in velocity and position of a minute particle in space are 2.4 times 10 to the power minus 26 meter per second and 10 to the power minus 7 meter respectively, then what is the mass of the particle in gram is? We have to find out the nearest integer. Planck constant value is given. As per Heisenberg's uncertainty principle, we know that it is impossible to accurately determine both the position and the momentum of a microscopic particle simultaneously. The product of uncertainty, that is the error in measurement, is expressed by this equation, that is delta x times delta p should always be greater than or equal to Planck constant divided by 4 pi. Now here the uncertainty in velocity is given. We know that momentum is mass times velocity. Therefore, delta p is mass times delta v. That is given as 2.4 times 10 to the power minus 26. Uncertainty in position is also given. So, let us plug in those values. Let us rewrite this equation this way. M times delta v times delta x is greater than or equal to h by 4 pi. So, m we need to figure out. Delta v value is 2.4 times 10 to the power minus 26 meter per second. Delta x value is 10 to the power minus 7 meter greater than or equal to 6.626 times 10 to the power minus 34 kilogram meter square per second. The reason is 1 joule is equal to 1 kilogram meter square per second square. So, the Planck constant's unit is joule second and 1 joule is this much, and that is how we come here. So, this is divided by 4 pi. Let us cancel the units that are common. Here we have meter per second and then meter. So, that is meter square per second. So, we can cancel that. Here also we have meter square per second. So, we can cancel on this side. So, only kilogram will remain. That is the unit for the mass. But finally, we need to convert it in gram. And we have 10 to the power minus 26 here, 10 to the power minus 7 here. So, that together will become 10 to the power minus 33. We have 2.4. So, on this side we have 10 to the power minus 34. So, if we cancel that, then this will become 10 to the power minus 1. So, therefore, we can write that mass is greater than or equal to 6.626 times 10 to the power minus 1 kg divided by 4 times 2.4. 4 times 24 is 96. So, 9.6 times pi. Now, pi value is 3.14. So, let us take the pi value as approximately 3 and this one approximately as 9 and this one approximately as 6. So, in that case what will happen is mass is equal to 6 by 27 because 9 times 3 times 10 to the power minus 1 kg. So, this will be 2 by 9. So, we can't divide 2 by 9. So, let us add a 0. So, 0.2 times 9 is 18, remaining 2, again we can't divide. So, put a 0. So, this will be keep going 0.222. So, 0.222 times 10 to the power minus 1 kilogram. So, if we convert the kilogram into gram, then 10 to the power 3 gram. This will become 10 to the power 2. So, therefore, 22.2 gram. So, approximately the mass of the particle is 22. An electron of helium plus is present in third excited state, find its de Broglie wavelength. We know that de Broglie wavelength lambda is equal to Planck constant h divided by mv. We also know from Bohr's theory that electron can revolve only in those orbits in which the angular momentum, that is mvr of the electron, must be equal to an integral multiple of h divided by 2 pi. Let us equate these two equations. If we do that, then we can write that 2 pi r is equal to n times h by mv. Therefore, 2 pi r is equal to n times lambda. So, 2 pi r is the circumference. What equation 3 means is that in order for the electron wave to exist in phase, the circumference of the orbit should be an integral multiple of the wavelength of the electron wave. We also know that Bohr's radius Rn is equal to 0.529 times n square divided by z, the atomic number, and the unit is angstrom. Here in the question it is mentioned as third excited state. Therefore, the n value is equal to 4 here. For n equal to 1 means it is ground state. N equal to 2 means that is the first excited state. It is easy to make a mistake thinking that n value equal to 3. N equal to 3 means that is second excited state. N equal to 4 means that is the third excited state. Therefore, the n value is 4 here. Therefore, we can write that lambda from these equations, we can write that lambda is equal to 2 pi times 0.529 times n square divided by z times n. For helium, the z value is 2 because the atomic number is 2. And therefore, this is equal to 2 pi times 0.529 times n value is 4, and therefore 4 square is 16 divided by 2 times 4. This 2 will cancel. This is 4 times 4, therefore 4. Pi value is 3.14 times 0.529 times 4. Let us take this as approximately 3, this as approximately 0.5. So, in that case this is 1.5. 1.5 times 4 is 6, and therefore, lambda should be approximately 6 point something angstrom should be our answer. Therefore, 6.64 angstrom is the correct answer. So, option A is correct. What is the ratio of the shortest wavelength of Balmer series to the shortest wavelength of Lyman series of hydrogen atoms? As per Bohr's model, we know that energy for the nth stationary state is equal to minus Rydberg constant times z square divided by n square. Rydberg constant value is equal to 13.6 eV. Z is the atomic number. In the case of hydrogen atom, it is 1 because for hydrogen atom atomic number is 1. And n is the value of the stationary state. So, it is the energy difference that we calculate, that is delta E is equal to En2 minus En1, and that is equal to minus Rydberg constant times 1 by N2 square minus 1 by N1 square. N2 value should always be greater than N1. Now, let us say we have several stationary states. When we say something as a Lyman series, if an electron that has gone to the excited state falls back to the ground state, then we call that as a Lyman series, for which n value is equal to 1, that is ground state. When we say something as a Balmer series, if an electron that has gone to the excited state falls back to the first excited state, then we say that that is a Balmer series, for which n value is equal to 2. But here they are asking
shortest wavelength. This means that the n value has to be infinity, because energy and wavelength are inversely proportional as per this equation. Therefore, if we have to get the shortest wavelength, then the energy gap has to be the highest. So when it would be highest? Only when the n value is equal to infinity. But when the n value is infinity, when the electron is here, what would happen to the energy? Energy would become zero, because we are basically hitting the continuum. There won't be any interaction between the nucleus and the electron. So therefore, mathematically, when the n value is infinity, energy would become zero, which means shortest wavelength of the Lyman series, it is the energy of the state itself. That's what we need to understand. And when we say Balmer series, it is the energy of the state itself. So therefore, we can calculate it this way: Hc divided by lambda b to specify the Balmer series is equal to minus Rydberg constant times 1 by infinity square, which would be 0, minus 1 by n1 value, in this case is 2, because it is Balmer series. So 2 square is 4. So therefore, this would be equal to simply Rydberg constant divided by 4, because minus into minus will become plus, 1 by infinity square is 0. So that is one equation. And the other equation is Hc by lambda L, and that would be equal to minus Rydberg constant times 1 by infinity square, once again that is 0, minus 1 by n1 square. n1 value now is 1. So therefore 1 by 1 square, and that is equal to simply 1. So therefore this is equal to simply Rydberg constant. Let's keep this as equation 2. Now what they are asking? Ratio of the shortest wavelength of Balmer series to the shortest wavelength of Lyman series of hydrogen atom. Therefore, Hc divided by lambda b whole divided by Hc divided by lambda L is equal to what? And this would be equal to Rydberg constant divided by 4 whole divided by Rydberg constant, which we can write it as Rydberg constant divided by 4 times 1 by Rydberg constant, because this is basically Rydberg constant divided by 1. So we can write it this way. Common terms we can cancel. So this means 1 by lambda b divided by 1 by lambda L is equal to 1 by 4, which we can write it as 1 by lambda b times lambda L divided by 1, and that is equal to 1 by 4. So basically lambda L divided by lambda b is equal to 1 by 4. But that is not what they are asking. The reverse of it. The reverse of it is lambda b divided by lambda L, we need to find out. So therefore that is equal to 4 by 1. So which means 4 is to 1. That is the correct answer. Therefore option 1 is correct.
For hydrogen-like species, which of the following graphs provides the most appropriate representation of energy versus atomic number plot for a constant n value? E is the energy of the stationary state, Z is atomic number, and n is the principal quantum number. For hydrogen-like species, the energy of the stationary state is equal to minus Rydberg constant times Z square divided by n square, or we can also write it as minus 13.6 Z square divided by n square. If we keep n equal to 1, then we can write it as energy is equal to minus 13.6 times Z square. This is in the form of y is equal to minus ax square. So it's a simple quadratic function with a negative sign, and therefore option 2 should be correct. All other options are wrong, because this is in the form of y is equal to minus x, this is in the form of y is equal to plus x, this is in the form of y is equal to ax square. Therefore option 2 is the only choice that should be correct.
Consider the ground state of chromium. How many electrons are there
with the azimuthal quantum number L equal to 1 and L equal to 2 respectively. Let us first write the electronic configuration of chromium. Atomic number is given as 24. Therefore, we have 24 electrons. Therefore, the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. We do not write 4s2, 3d4 because half filled and completely filled d orbitals are more stable due to higher amount of exchange energy. It is not like we are violating the half-bulk principle here. We are deviating from the half-bulk principle because this is a more stable electronic configuration than 4s2, 3d4. So therefore, for chromium, we have to write it as 4s1, 3d5. Likewise, for copper, we have to write 4s1, 3d10. So now let us come to the azimuthal quantum number. We know that azimuthal quantum number is 0 for s orbital. If it is 1, it means it is p orbital. If it is 2, it means it is d orbital. If it is 3, it means f orbital. Now, we don't have to worry about s orbitals in this case. So, we have to worry about only p and d orbitals. Here we have 6 electrons. Here we have 6 electrons. So, altogether it is 12 when L equal to 1. And then in 3d5 we have 5 electrons where L value is equal to 2. So, therefore, option 3 is the correct choice here. A spectral line will be observed for a 2px to 2py transition. Think about it in terms of quantum numbers. Here the principal quantum number value will be equal to 2 and here also it will be equal to 2. Think about hydrogen emission spectrum. The energy in that case is equal to minus Rydberg constant times z square divided by n square. Z is the value of the atomic number. For hydrogen atom it is equal to 1 and n is the value of the stationary state. Therefore, the energy difference delta E is equal to minus Rydberg constant times 1 by n2 square minus 1 by n1 square. If n2 is equal to n1, then how you will observe a spectral line? You won't, because delta E is equal to 0, therefore no spectral line. This means that statement 1 is false. How about statement 2? 2px and 2py are degenerate orbitals. In absence of external fields such as electric or magnetic, they are indeed degenerate because the energy will be one and the same. Therefore, statement 2 is true. Statement 1 is false, but statement 2 is true, and that is mentioned in option 4. Hello everyone, here's a question based on quantum numbers. Quantum number for outermost electron of potassium atom are given by which of the following? We know that for potassium atomic number is 19, that means we have 19 electrons. Therefore, the electronic configuration is argon that has 18 electrons and then 4s1. For this electron, we need to find out all the 4 different quantum numbers. Since it is 4s orbital, the principal quantum number is equal to 4. When the principal quantum number is 4, the azimuthal quantum number or angular momentum quantum number actually runs from 0 to n minus 1. Therefore, it can have 4 different values 0, 1, 2, 3. However, for a 4s orbital, the L value is equal to 0. For s orbital, the L value is 0. For p orbital, the L value is 1. For d orbital, the L value is 2. And then for a f orbital, the L value is 3. So therefore, we have to take L value as 0 because it is a 4s orbital. And then ML values, the magnetic quantum number, that runs from negative L to positive L including 0. So if L value is equal to 0, then obviously ML value will also be 0. And then the spin quantum number will be equal to plus half because there is only one electron here, so we can consider it as up spin. Therefore, option 1 is the correct choice here. In a multi-electron atom, which of the following orbitals described by 3 quantum numbers will have the same energy in absence of electric and magnetic fields? That means no Stark effect, because if the electric field is absent, no Stark effect, and if the magnetic field is also absent, then it means no JEEMAIN effect. We know that JEEMAIN effect provides the experimental justification for the magnetic quantum number. That means these values are irrelevant here, isn't it? Because if the JEEMAIN effect is not there, then magnetic quantum number is not there. Therefore, let us decide the orbital designation. N equal to 1, L equal to 0. This means 1s orbital, because L equal to 0 means s orbital. N equal to 2, L equal to 0. This means 2s orbital. N equal to 2, L equal to 1. This means 2p orbital, because L equal to 1 means p orbital. N equal to 3, L equal to 2. This is 3d. N equal to 3, L equal to 2 once again. This is also 3d. This means these two are degenerate. Therefore, D and E will have the same energy. This means option 4 is correct. How many orbitals have the following set of quantum numbers n equal to 4, ml equal to 0? Magnetic quantum number ml depends on angular momentum quantum number L. Angular momentum quantum number L depends on principal quantum number n. When the n value is equal to 4, how many L values we will have? We will have 4 different L values, isn't it? They are 0, 1, 2 and 3, because L runs from 0 to n minus 1. What will happen to the ml values? Ml values runs from minus L to plus L through 0. So this means each L value will have a ml value equal to 0, isn't it? Because when L equal to 0, ml value will be simply 0. When L equal to 1, ml value will be minus 1, 0, plus 1. When L equal to 2, ml values will be minus 2, minus 1, 0, plus 1, plus 2. When L equal to 3, ml values will be minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. So in each case we have a 0. So this means we have 4 orbitals. Therefore option 4 is correct. Here we have 4s, here we have 4p, here we have 4d, here we have 4f orbitals, but specifically they want n equal to 4 and ml equal to 0. So therefore we should count it as 4 orbitals. Therefore option 4 is correct. What are the correct statements for an element with atomic number 9? We know that fluorine's atomic number is 9. That means it has 9 electrons, and therefore the electronic configuration is 1s2, 2s2, 2p, 5. 1s2 has 2 electrons, 2s2 has 2 electrons, and 2p5, 2p has 3 orbitals. So we can fill up electrons this way: 1, 2, 3, 4 and then 5. Now think about how we can differentiate the 1s2 electrons. The only way we can differentiate 1s2 electrons is through the spin quantum number, because all other quantum numbers are equal. N equal to 1, L equal to 0, ml equal to 0, and one electron will have spin quantum number plus half up spin, and another electron, the second electron that we put inside 1s2, will have down spin. That's what the Pauli exclusion principle says, isn't it? No two electrons in an atom can have the same set of values for all 4 quantum numbers. Likewise for 2s2, but here the n value is equal to 2. And likewise for 2p, here the n value is 2 but the L value is 1 because it is p orbital. And then the ML values will be minus 1, 0, plus 1. We can differentiate these two electrons with the spin quantum number and these two electrons with the spin quantum number, and this one is up spin. Therefore, in total we have 5 electrons with up spin and 4 electrons with down spin. Therefore, statement A is definitely correct. Now, statement B indicates that there is only one electron in pz orbital. Though it appears correct, such a generalization is not correct because assigning px, py, pz symbol to 2p orbitals is quite arbitrary. We can even put this way: py, px, pz, or pz, py, px. So this is quite arbitrary. Therefore, statement B is an incorrect generalization. Therefore, B is definitely wrong. And then statement C says the last electron goes to orbital with n equal to 2, L equal to 1. This is correct because here they are talking about this electron. So, if we are taking this electron into account, the principal quantum number is 2 and the angular momentum quantum number is 1. Therefore, statement C is definitely correct. Now, how about statement D? The sum of angular nodes of all atomic orbitals is 1. Is that correct? No, it is not correct. Angular nodes depends on the value of L, but in 2p we have 3 2p orbitals. So, for each p orbital, if we assign angular node as 1 each, then that sum will be 3. So, therefore, it won't be equal to 1. S orbitals, L values are 0. For 2s also, L value is 0. But if we are taking the 2p orbitals into account, then each orbital has one angular node. 2px has one angular node, 2py has one angular node, 2pz has one angular node. So, therefore, statement D is definitely incorrect. So, this means option 3 is the correct choice here. 4 different elements are given in list 1 and the electronic configurations are given in list 2. We need to match these two and find out the correct answer. This is more of a memory based question. So, if you remember the atomic number of different elements, then you can easily write the electronic configuration. Even if you remember the atomic number of 2 different elements, you can find out the correct answer. So, for example, I remember the atomic number of nitrogen, that is 7. Atomic number in a neutral element is equal to the number of protons and number of electrons. So, therefore, the electronic configuration for nitrogen is 1s2, 2s2, 2p3. We have 7 electrons here in total. So, this means Q should match with 3. This means 1 is wrong, 2 is also wrong. And I also remember that for argon the atomic number is 18. Therefore, the electronic configuration has to be 1s2, 2s2, 2p6, 3s2, 3p6. So, this means that S should match with 4. Therefore, option 4 is the correct choice. Atomic number for sulfur is 16 and for krypton it is 36. These two things will match. R will match with 2 and P will match with 1. So, therefore, option 4 is correct. The electronic configuration of 4 different transition metal ions are given and we need to match them and figure out the correct answer. For manganese, we know that atomic number is 25 and for vanadium atomic number is 23 and for chromium atomic number is 24 and for iron atomic number is 26. Let us first figure out for chromium because that is a tricky case. When it is neutral, the electronic configuration is going to be argon that has 18 electrons and then 4s1 3d5. We write it this way for chromium because half filled and completely filled d orbitals are more stable due to exchange energy. This is a slight deviation from the Aufbau principle. Now, when we remove one electron, so when it is chromium plus, we are removing one electron. So therefore, now we have 23 electrons in total. Therefore, the electronic configuration would be argon and then 3d5, because here the principal quantum number is 4. This is the outer shell. Therefore, we need to remove electrons from here. So therefore, for chromium plus, it would be 3d5 4s0. That is given in option 2. So therefore, C should match with the 2, isn't it? Now let's figure out for manganese. For neutral manganese, the electronic configuration is going to be argon 18 electrons and then 4s2 20 and then 3d5. But when it is manganese 2 plus, we are going to have only 23 electrons. So this means the 4s2 electrons will be removed. So therefore, we will be having 3d5 4s0. So therefore, A also should match with the 2. Where it is given where C is matching with the 2 and A is also matching with the 2, that option is given only in 3. So therefore, option 3 should be correct. For vanadium, if it is neutral, then the electronic configuration will be argon and then 4s2 3d3. When it is vanadium plus, we will be removing one electron from the 4s orbital. So therefore, it would become, when it is vanadium plus, it would become 4s1 3d3. So B should match with 1. So it is matching. How about Fe2 plus? So Fe2 plus, we would be removing 2 electrons from 4s2. So therefore, it is obviously 3d6. So therefore, option 3 is the correct choice here. 5 successive ionization energies of an element are given and we need to figure out which group the element belongs to. We do see a sudden spike in value for the 4th ionization energy. We do see a huge number for the 5th one. And this means that here we are trying to knock out the core electrons, whereas these values corresponds to the valence electrons. Boron has 3 valence electrons, 1s2, 2s2, 2p1. We have 3 valence electrons here, and therefore when we try to knock out the core electrons, the ionization energy is increasing tremendously. We know that carbon belongs to group 14 and that means boron belongs to group 13. Boron, aluminium, gallium, indium, all those elements belong to group 13 and therefore group 13 is the correct choice here. Therefore option 2 is correct. What is the correct increasing order of the ionic radii is? Increasing order means we need to write down the smallest value first. Let us first write down the atomic numbers. Sulfur atomic number is 16. For chlorine atomic number is 17. For potassium atomic number is 19. And for calcium atomic number is 20. Here 4 different ions are given. S2 minus will have 18 electrons because 16 and we have to add 2 more electrons for the 2 minus charge. And then Cl minus will also have 18 electrons, 17 plus 1 electron, and then potassium plus, that would have 18 electrons as well because 19 minus 1. For the positive charge we need to remove 1 electron. Likewise for Ca2 plus we would have 18 electrons. So this means all the species given here are isoelectronic species. So in the case of isoelectronic species, the size is proportional to 1 by Z. Z is the atomic number. If the Z value is increasing, then the size will decrease, because when the Z value is increasing, we have more number of protons. The positive charge is increasing. Therefore, the size has to decrease.
So this means calcium 2 plus should be written first, and then potassium plus, and then Cl minus, and then S2 minus. That should be the correct order, which is given in option 4. Therefore, option 4 is correct.
Electronic configuration of 4 elements are given, and they are asking which of the following is the correct order of increasing electronegativity in terms of Pauling scale. We know that in a neutral element, the number of protons must be equal to the number of electrons. So based on the number of electrons, we can determine the atomic number. Here we have 1s2, 2s2, 2p3. Therefore total 7 electrons we have. Therefore this belongs to nitrogen. Here we have 1s2, 2s2, 2p4. Therefore total 8 electrons, and this belongs to oxygen. Here we have 1s2, 2s2, 2p5. That means 9 electrons in total. Therefore this belongs to fluorine. And in option D we have 1s2, 2s2, 2p2. 6 electrons in total, therefore that belongs to carbon. Now in the periodic table, electronegativity increases when we go from left to right, and within a group it decreases. So therefore which one will have the lowest value? Carbon will have the lowest value. So we are writing in ascending order. So therefore carbon first, and then nitrogen, and then oxygen, and then fluorine. So electronegativity will increase from carbon to fluorine. So therefore D should come first, and that is less than A, and that is less than B, and that is less than C, which is given in option 2. Therefore option 2 is correct. Which one of the following sets of ions represents a collection of isoelectronic species? When we say something as isoelectronic, if the number of electrons are same, then we can say something as isoelectronic. For a neutral element, the number of protons will be equal to the number of electrons. So in this question, certain atomic numbers are given, certain atomic numbers are not given. So for example, the atomic number of barium and strontium are not given, but we know that they both belong to the same group, calcium as well, group 2. But potassium belongs to group 1. So therefore they will not be isoelectronic. So we can rule out this. And then for option 1, lithium atomic number is 3, but it is Li plus. Therefore we will have 2 electrons. And sodium belong to the same group. Atomic number is 11, but it is Na plus. So we will have 10 electrons. Therefore we don't need to check about magnesium 2 plus and calcium 2 plus, because they are not going to be isoelectronic. So even if we do check, we would get 10 for magnesium 2 plus, and for calcium 2 plus we would get 18, because for calcium the atomic number is 20. And then for number 3, nitrogen atomic number is 7, so 3 minus, that means 10 electrons. Oxygen atomic number is 8, but oxygen 2 minus, therefore 10 electrons. F minus, atomic number of fluorine is 9, therefore 10 electrons. Sulfur 2 minus, atomic number of sulfur is 16, which is not given here, but we know it. So sulfur 2 minus, 18 electrons. Therefore this is also not correct. By the way, you can also rule out option 3, because oxygen and sulfur belong to the same group and the charges are same. So in case if you do not remember the atomic number of sulfur, you can still rule out that. And then for option 4, potassium plus, K plus, so 19 is the atomic number, therefore we will have 18 electrons. Chlorine atomic number is 17, but Cl minus, therefore 18 electrons.
calcium 2 plus 18 electrons, scandium 3 plus, atomic number for scandium is 21, so we are removing 3 electrons. That means that will also have 18 electrons. Therefore, option 4 is correct.
Number of water molecules in washing soda and soda ash respectively are how many? We know that sodium carbonate is referred as soda ash. Sodium carbonate is Na2CO3, that will not have any water molecules. So this means 4 is wrong, 2 is also wrong. Soda ash, when we dissolve in water and then recrystallize it, we would get washing soda, that is sodium carbonate decahydrate. It would have 10 water molecules. The crystal will have 10 water molecules, that is washing soda. So this means option 3 is correct. X gram of molecular oxygen is mixed with 200 gram of neon. The total pressure of non-reactive mixture of O2 and neon in the cylinder is 25 bar. The partial pressure of neon is 20 bar at the same temperature and volume. What is the value of X is? We need to find out the mass of O2 here. Let's keep that one as X. We know that number of moles is equal to mass divided by molar mass. So therefore, X divided by 32, number of moles of O2, because molar mass of O2 is 32 gram per mole. Now, total pressure here is given as 25 bar and the partial pressure of neon is given as 20 bar. In that case, what would be the partial pressure of O2? 25 minus 20. So therefore, 5 bar. Because in the cylinder, the total pressure is 25 bar. That means this is a mixture of O2 plus neon, isn't it? So therefore, the partial pressure of O2 should be 5. Now, we also know that partial pressure of an entity is equal to mole fraction times total pressure, isn't it? So mole fraction of O2 is equal to number of moles of O2 divided by total number of moles of O2 plus neon. So therefore, this is equal to X divided by 32 whole divided by X divided by 32 plus mass of neon 200 gram divided by molar mass of neon, that is 20 gram. So therefore, 5 equal to mole fraction of O2 times 25. So this one we have already figured out. Let's insert that. So which means 5 equal to X by 32 whole divided by X by 32 plus 200 by 20 times 25. So this will be 5 times. Let's bring the 5 on the other side. So 1 by 5 equal to, this will be 10 times X by 32 whole divided by X by 32 plus 10. So this expression in the denominator we can write it as, if we take 32 as common, then it would be X plus 320, isn't it? So therefore 1 by 5 equal to X by 32 divided by X plus 320 divided by 32. So therefore this is equal to X times 32. I am sending this 32 up, this one I am bringing here, divided by 32 times X plus 320. So 32 we can cancel. So this means if we send on the other side, X plus 320 equal to 5X, isn't it? So therefore 320 equal to 4X, therefore X is equal to 320 divided by 4, and that would be 80. So 80 gram That is the correct answer. So therefore, the value of X is AD. That's the correct answer. The enthalpies of formation of CCl4, H2O, CO2 and HCl are given. What is the magnitude of enthalpy of the reaction given below is in terms of kilojoules per mole. First of all, is the equation is balanced? Yes, it is balanced. And we know that the heat of formation of the reaction or enthalpy of formation of the reaction is equal to sum of enthalpy of formation of products minus sum of enthalpy of formation of the reactants. All the values are given and therefore let's substitute those values. On the product side we have CO2 and HCl. So CO2 is 1 mole but HCl is 4 moles and therefore 1 times minus 394 and then plus 4 times minus HCl, that is minus 92 kilojoules per mole, minus this is for the products. Now let's go to the reactants. So for reactants CCl4 is 1 mole but water is 2 mole. So for CCl4 it is 1 times minus 105 and then for water it is 2 times minus 242. So therefore this will be equal to minus 394 and then 4 times 92. 4 times 92 is 368 but we have minus and therefore minus 368 and then again minus and then minus 105 again minus 2 times 242, that will be 484. So therefore this will be equal to minus 394 minus 368. So 8 plus 4 2 and then 10 plus 6 16, so 6 remaining 1 and then 3 plus 3 6 plus 1 7, so minus 762 and then this minus into minus will become eventually plus and this will be 589 if we add 105 and 484. So 762 minus 589, so 12 minus 9 3, here it will become 5, so 15 minus 8 7, so we have 6 here, 6 minus 5 1, so minus 173 kilojoules per mole. That's the enthalpy of the reaction. However, here they have asked the magnitude of enthalpy of the reaction. Therefore, we must enter it as 173 and not minus 173. So this part you need to be careful because the reaction is actually exothermic. The negative sign implies that it is exothermic. But in the question they have asked only the magnitude of enthalpy. Therefore, we have to enter only the numerical value. We have to ignore the sign. Consider the following cases of standard enthalpy of reaction and figure out the magnitude of standard enthalpy of formation of C2H6 gas. We need to figure out the answer but write only the magnitude. So this means that if we have a negative sign then we should ignore it. And we have to find out the answer in kilojoules per mole. We have to find out the answer, the nearest integer. Now, the standard heat of formation or standard enthalpy of formation of a compound is defined as the change in enthalpy that takes place when 1 mole of a compound is formed from its elements present in their standard states under standard conditions. So this means we have to consider 1 mole of C2H6 gas. How we can get 1 mole of C2H6 gas? If we have 2 carbon exists as graphite in the standard state and then hydrogen exists as H2 gas in the standard state, then we can get 1 mole of C2H6 gas. Now think about how we can get 1 mole of C2H6 from these 3 equations. Like basically how we can arrive at this equation using these 3 equations. What changes do we need to do? We have to multiply the second equation by 2 because we require 2 carbons, isn't it? So this entire equation we need to multiply by 2, and then the third equation we have to multiply by 3 so that we can get 3H2. And the first equation, the C2H6 is on the reactant side. So this means we need to reverse the equation. We need to bring it to the product side. So if we bring it to the product side, what will happen to delta H1? Delta H1 naught will become minus delta H1 naught, because if we are converting reactants into products and products into reactants, then we need to change the sign. Let me put it this way. So we have multiplied with all the factors. So if we have these three equations, so if we sum it up, then what will happen? We have 3 waters on the reactant side, we have 3 waters on the product side, that would cancel out. We have 2 moles of O2 on the reactant side and 3 by 2 moles of O2 on the reactant side. So if we sum it up, then that will be 7 by 2. So we can cancel that. And we have 2 moles of CO2 on the reactant side, 2 moles of CO2 on the product side. So if we sum it up, then we will get this equation: 2 times carbon plus 3 times H2 gas, and that would give us 1 mole of C2H6 gas. For that we are finding the standard heat of formation. So therefore the standard heat of formation for C2H6 gas is equal to minus delta H10 plus 2 times delta H20 plus 3 times delta H30. Therefore this is equal to 1550, because we have to change the sign, plus 2 times minus 393.5 plus 3 times minus 286. So therefore delta H formation standard is equal to 1550 minus 787 minus 858, and that is equal to 1550 minus 1645, and the answer we will get it as minus 95 kilojoules per mole. However, we have to enter only the magnitude. So that means 95 kilojoules per mole is the correct answer, not minus 95 kilojoules per mole. We have to enter only the magnitude. Therefore 95 is the correct answer. Consider the following data. Heat of formation of CO2 is given, heat of formation of water is given, and heat of combustion of benzene is given. We need to figure out the heat of formation of benzene. We can basically write 3 equations for this. Heat of formation is change in enthalpy when 1 mole of a compound forms from its elements in their standard states, and heat of combustion is change in enthalpy when 1 mole of a substance burns completely in oxygen to form stable oxides. So let us first write the heat of combustion of benzene, that would be C6H6. If this undergoes combustion, then we would get CO2 gas plus water. Now we have to balance this equation. We have 6 carbon atoms here, so therefore put 6 here. We have 6 hydrogen atoms, so therefore put 3 here, so that we would have 6 hydrogen atoms on the product side. Now on the product side we have 15 oxygen atoms, isn't it? 6 times 2 plus 3, that means 15 by 2 of O2. Now this equation is balanced. Let us write 2 equations for the heat of formation of CO2 and water. So that is graphite reacting with O2 giving CO2 gas. For this one we have the data, and then H2 gas reacting with half a mole of O2 giving water. For this one also we have the data. For the heat of formation of benzene, what equation we can write? If we say 6 carbons graphite plus 3H2 gas, that is C6H6. Now how we can get to this equation from these three equations? We have to reverse equation 3 at least, isn't it? So that the benzene will be on the product side. So let's do that first. 6 times CO2 plus 3 times H2O giving C6H6 plus 15 by 2 O2. So this means the delta H value we need to change it now. So this would become plus, isn't it? 3267. Because if we are changing products into reactants, then we need to change the sign, and we have to multiply the first equation by 6. So this will be 6 times carbon, 6 times O2, 6 times CO2, and then the second one we have to multiply with the 3, so that if we sum up we can get this one. So 3 times H2, 3 by 2 times O2 and 3 times water. So now if we sum up we can cancel the common things. 6 times CO2, 6 times CO2, 3 times water, 3 times water, and then 15 by 2 times O2, that we can cancel. 6 times O2 here plus 3 by 2 O2. So together that will be 15 by 2 O2. So now the remaining terms are this one. So this means heat of formation for benzene is equal to 3267 plus 6 times minus 393.5 plus 3 times minus 286. If it is 400, it would be 2400. So 6.5 times 6, that will be 39. So that means this will be 2361 minus 2361. So therefore this is minus 2361, and then minus 286 times 3, that will be 858. So if we are adding 858 here, then it will be 9, 6 plus 5, 11, remaining 1, 8 plus 3, 11 plus 1, 12, remaining 1. So 3219. So 3219 we need to subtract here. 17 minus 9, 8, 5 minus 1, 4. So it would be plus 48 kilojoules per mole. That is the correct answer. So therefore 48 kilojoules per mole is the correct answer. For the given hypothetical reactions, the equilibrium constants are as follows. In that case, what is the equilibrium constant for the reaction between X and W? Basically, they are asking what is the equilibrium constant for the net reaction. This means that we can combine these three. When we combine these three, these will cancel, and what we are going to get is X and W. When we are combining the individual equilibria, we need to multiply the equilibrium constants, because when we write individually, this is equal to products raised to the respective stoichiometric coefficient. Here stoichiometric coefficient is 1 for everything. So this is concentration of Y divided by concentration of X, and K2 is concentration of Z divided by concentration of Y, and then K3 is concentration of W divided by concentration of Z. This means that K4 is equal to K1 times K2 times K3. So if you write it this way, Y divided by X times Z divided by Y times W divided by Z. We can cancel this. We can cancel this. So what we got is W divided by X. So this means 1 times 2 times 4, that is equal to 8. K4 is 8, which means option 4 is correct. Consider the given equilibrium reaction. If initial pressure of CO2 is 0.6 atm and after equilibrium is established, total pressure is 0.8 atm. In that case, find the value of Kp. First of all, this is a heterogeneous equilibrium because one of the reactants is in solid phase and one is in gas phase. Therefore, the concentration of pure solid is a constant because it has the same concentration at a given temperature. It doesn't expand to fill its container. Therefore, when we write the Kp value here depends on CO and CO2, not the carbon solid. Therefore, Kp is equal to partial pressure of CO whole square, because we have the stoichiometric coefficient 2 here, divided by partial pressure of CO2. Now, when T equal to 0, the pressure of CO2 is given as 0.6 atm. When T is equal to T equilibrium, then this becomes 0.6 minus P and this will be 2P. Total pressure is given as 0.8 atm, that is 0.8 at equilibrium. Therefore, this is equal to 0.6 minus P plus 2P. Therefore, this will become 0.6 plus P. So, 0.8 equal to 0.6 plus P. Therefore, P is equal to 0.2, isn't it? We know that Kp is equal to partial pressure of CO whole square divided by partial pressure of CO2. Partial pressure of CO is 2P. Therefore, 2P whole square divided by partial pressure of CO2 at equilibrium is 0.6 minus P. We know the value of P. Therefore, this is 2 times 0.2 whole square divided by 0.6 minus 0.2. Therefore, this will be equal to 4 times 0.04 divided by 0.4. Let us write it this way. 4 times 4 times 10 to the power minus 2 divided by 4 times 10 to the power minus 1. This will cancel. Therefore, this is simply 4 times 10 to the power minus 1. That means this is equal to 0.4. Kp value is 0.4. This means option 1 is correct. Ammonium carbamate solid is getting dissociated as ammonia and CO2 gases. If the partial pressure of CO2 gas at equilibrium is 0.4 atm and the total pressure is 1 atm, then the value of Kp at the same temperature would be how much? First of all, this is a heterogeneous equilibrium because a solid is getting dissociated as gases. Therefore, the partial pressure or the concentration of pure solids should be taken as a constant. Therefore, Kp in this case should be written as partial pressure of ammonia to the whole square, because we have the stoichiometric coefficient 2 here, times partial pressure of CO2. Partial pressure of CO2 here is given as 0.4 atm and the total pressure is mentioned as 1 atm. Therefore, 1 minus 0.4 is 0.6 atm. The partial pressure of ammonia should be taken as 0.6 here. Therefore, 0.6 square times 0.4. Therefore, this is equal to 0.36 times 0.4. Therefore, this will be equal to 0.144 atm cube. That should be the correct answer. This means option 3 is correct. At 298 K, we have the following equilibrium reactions. Based on the above equilibria, we need to find out the equilibrium constant for the net reaction. We need to find out the integer times 10 to the power minus 33. Now, in the net reaction, we see ammonia on the reactant side. Here, we see ammonia on the product side. Therefore, if we reverse this, then we can get ammonia on the reactant side. So, if we are reversing this equation, then we can write that 2 times ammonia giving N2 plus 3 times H2. So, this means K1 prime is equal to 1 by K1. So that is one reaction. And then we do see NO on the product side and water on the product side. However, here we have 3 as the stoichiometric coefficient. Therefore, this entire thing if we multiply by 3, then we can get 3 times water. So let's do that. So 3 times H2 gas plus 3 by 2 O2 giving 3 times water. So this means K3 should be cubed, not 3 times K3, because when you write K3, simply K3 in terms of partial pressure, this is partial pressure of water divided by partial pressure of H2 times partial pressure of O2 to the whole power 1 by 2. For this, if you write the same expression, then it would be partial pressure of water to the whole power 3, because we have 3 as the stoichiometric coefficient, divided by partial pressure of H2 to the whole power 3 times partial pressure of O2 to the whole power 3 by 2. Now, from here, how we can get to this expression? We can get to this expression if we write like this: partial pressure of water divided by partial pressure of H2 times partial pressure of O2 to the whole power 1 by 2 to the whole power 3, isn't it? So this means, so this is K3, so K3 to the whole power 3. So that's why I have written K3 to the whole cube, not 3 times K3. You shouldn't simply multiply by 3. Now, so if we add this one and this one, we can get this one, because we have 2 times ammonia, and then this is 1 times O2, this is 3 by 2 times O2. So basically we are adding up. So let's say this is equation 1, this is equation 2, and this is equation 3. So 1, 2, 3, if we add all of them, we can get this. N2 will cancel, because N2 here is on the product side and here N2 is on the reactant side. So therefore they will cancel. Likewise, H2 is also on the product side as well as on the reactant side. Therefore that would also cancel, and everything else you can get. So this means the equilibrium, K equilibrium now is equal to K1 prime times K2 times K3 to the whole cube. K1 prime is 1 by K1, isn't it? So therefore, let's write it this way: K equilibrium is equal to K2 times K3 to the whole power 3 divided by K1. So therefore, K2 is 1.6 times 10 to the power 1.6 times 10 to the power 12, that is K2, and then K3 is 1 times 10 to the power minus 13 to the whole power 3 divided by K1 is 4 times 10 to the power 5. So here 10 to the power 12, this will become 10 to the power minus 39. When this one comes up, it will be 10 to the power minus 5. So this will become 10 to the power minus 44 and 10 to the power 12. So this means 10 to the power minus 32, isn't it? So we have 10 to the power minus 32. So this is 1.6 divided by 4 times 10 to the power minus 32. Now we have 10 to the power, they are asking in terms of 10 to the power minus 33. So this means what we can do is, let us make this one as 16 divided by 4. Then we can write it as 10 to the power minus 33. So this means 4 times 10 to the power minus 33. That's the correct answer. So that means 4 is the correct answer here. What is the volume of 3 molar NaOH which can be prepared from 84 gram of NaOH is in terms of 10 to the power minus 1 decimeter cube? We know that 1 liter is equal to 1 decimeter cube or cubic decimeter, whichever the way you want to call it. Concentration is equal to number of moles divided by volume. Concentration here is given in terms of molarity or moles per liter. We need to first figure out the number of moles here so that we can find out the volume. Number of moles is equal to mass divided by molar mass. Here what they mean by formula weight is basically molar mass, and therefore that is equal to weight given is 84 gram divided by molar mass is 40 gram per mole for NaOH, and therefore this is 21 divided by 10, and that is equal to 2.1 mole. Therefore volume is equal to 2.1 mole divided by concentration, that is given as 3 molar, therefore 3 mole per liter. Therefore this is equal to 0.7 liter, and that we can write it as 7 times 10 to the power minus 1 decimeter cube. So therefore 7 is the correct answer. 20 ml of 2 molar NaOH solution is added to 400 ml of 0.5 molar NaOH solution. What is the final concentration of the solution in terms of 10 to the power minus 2 molar? We need to find out the nearest integer. Here we have two different NaOH solutions. We are adding it together, whose molarity is different, volumes are also different, and we need to find out the final molar concentration. We know that number of moles is equal to molarity times volume in liter. Here the volume information is given in milliliters, therefore the number of moles that we calculate are actually millimoles. Therefore this is equal to molarity times volume in milliliter. We have two different solutions, therefore n plus n2 is equal to m1 times v1 plus m2 times v2. m1 is 2 molar, so 2 mole per liter, times v1 is 20 ml, and plus m2 is 0.5 molar, 0.5 mole per liter, times 400 milliliter. Therefore this is equal to 2 times 20, that is 40 millimoles, plus 0.5 times 400, that will be 200 millimoles. Therefore this total is 240 millimoles. Now we know that concentration or molar concentration is equal to number of moles of solute divided by volume in liter. Here the total number of moles we have in millimoles and the volume we have in milliliter, and the n value we have is 240 millimoles. Volume, total volume is 400 plus 20, therefore 420 milliliter. Milli will cancel, 1010 will cancel, and this will be 12 divided by 21 mole per liter. Let's divide 12 by 21. We can't divide it, therefore let's add a 0. 5 times will be 105, remaining 15 we can divide it, add a 0 again. 7 times will be 147, remaining 3 we can't divide, add a 0 once again, 1 time will be 21, remaining 9. Therefore, this will be equal to 0.571 molar, and that we can write it as 57.1 times 10 to the power minus 2 molar. Therefore, the nearest integer is 57. Therefore, the correct answer here is 57. 20 ml of sodium iodide solution gave 4.74 gram of silver iodide when treated with the excess amount of silver nitrate solution. What is the molarity of the sodium iodide solution is? We have excess amount of silver nitrate reacting with the sodium iodide, that gave us silver iodide plus sodium nitrate. The mass of silver iodide is 4.74 gram and the volume of sodium iodide is 20 milliliter. In terms of stoichiometric moles, if we have 1 mole of sodium iodide, we would get 1 mole of silver iodide. That's the stoichiometric mole ratio here. And we know that molarity is equal to number of moles divided by volume in liters. So, therefore, let us figure out the number of moles of silver iodide. Number of moles of silver iodide is equal to 4.74 gram divided by molar mass of silver iodide is 127 plus 108, that is 235 gram per mole. If I take this as 470 approximately times 10 to the power minus 2, then this is simply 2 times 10 to the power minus 2, that is 0.02. So, therefore, 0.02 mole. Therefore, molarity is equal to 0.02 mole divided by volume is 20 milliliter. Let us convert that into liters. So, therefore, 20 times 10 to the power minus 3 liter. So, this means this would also become 0.02. So, therefore, 0.02 divided by 0.02. So, this means 1 molar. That is the correct answer. Therefore, 1 is the correct answer here. Total number of molecules in which the central atom is sp2 hybridized is how many? We have 7 molecules given. So, let us find the hybridization one by one. The best way to do is to find out the steric number. Steric number is sum of sigma bonds plus sum of lone pairs. Therefore, for sp2 hybridization, the steric number has to be 3. If it is 4, then it is sp3. If it is 2, then it is sp. We have to figure out the molecules where the steric number will be 3. We can quickly do it through Lewis structure. So, for SiO2, the total number of valence electrons would be equal to 4 plus each oxygen has 6 valence electrons. So, 2 times 6, 12, and therefore, this will be 16 valence electrons. And therefore, the structure we can write it this way, the Lewis structure. Now, for the central atom silicon, we have only 2 sigma bonds. This is a sigma bond, this is a sigma bond. These two are pi bonds, isn't it? So, therefore, the steric number here is 2. Therefore, the hybridization for silicon in this case is sp. This means we need to omit this. And then for NH3, what would be the total number of valence electrons? It would be 5 plus 3 because atomic number of nitrogen is 7. So, 1s2 we shouldn't include and 2s2 2p3 electrons we are including. So, 5 plus 3 we have 8 valence electrons and the structure is gonna be this way: nitrogen and then 3 hydrogens with sigma bonds, and then we do have one lone pair. So, therefore, the steric number here is 3 plus 1 and that is equal to 4. This means here the hybridization is sp3. This means we shouldn't include this one also. How about CO2? What is the total number of valence electrons? 4 plus 12. So, we have 16 valence electrons once again, and the best Lewis structure would be this one. So this means once again we have steric number equal to 2. So therefore the hybridization of carbon here is sp. So we shouldn't include that one also. How about SO2? What is the total number of valence electrons here? Sulfur atomic number 16, and therefore 6 valence electrons we have. We have 2 oxygen atoms, therefore it is 12. So 6 plus 12, we have 18 valence electrons in SO2, and therefore the Lewis structure we can write it this way. Sulfur, and then we have a double bond with the oxygen, and then we do have a double bond with another oxygen, but now we have accounted for only 16 valence electrons. We still have one more lone pair that we can put on top of sulfur. So this means here we have 2 sigma bonds plus 1 lone pair. So the steric number here is 3. Therefore here the hybridization is sp2. This means we need to count SO2. And then C2H4, that is ethylene. So for C2H4, what would be the total number of valence electrons? 2 times 4 for carbon, that is 8, plus 4 for 4 hydrogens. So 8 plus 4, we have 12 valence electrons. So with 12 valence electrons, we can write a structure like this. We definitely do have a pi bond in ethylene because both the carbon atoms are sp2 hybridized. So this means that basically we have a p orbital here that can overlap sideways. That's how we get the pi bond. So we have a pi bond, we have a sigma bond, and all the carbon hydrogen bonds are also sigma. So for each carbon we have 3 sigma bonds, no lone pairs. So therefore here also the steric number is 3. This means both the carbon atoms are sp2 hybridized. So we need to count C2H4 also. How about C2H2, that is acetylene? In acetylene we will have how many valence electrons? We have 2 times 4, 8 plus 2, and therefore 10 valence electrons we will have. With 10 valence electrons we can write the structure like this. Hydrogen, and then carbon, and then triple bond, and then carbon, and then hydrogen. So this accounts for 10 valence electrons because we cannot put more than 2 valence electrons between carbon and hydrogen. So here also we cannot put more than 2 valence electrons between carbon and hydrogen. So we accounted for 4 valence electrons, and the remaining 6 valence electrons has to come between carbon and carbon. So therefore the hybridization here for both the carbon atoms is sp, isn't it? So we have 2 pi bonds. These 2 are pi bonds. We have 1 sigma bond here, 1 sigma bond here, 1 sigma bond here. So for each carbon atom we have 2 sigma bonds. That means the steric number in this case is 2. Therefore the hybridization is sp. So we shouldn't count C2H2. So we have to count SO2, we have to count C2H4. So in benzene we know that each carbon atom is sp2 hybridized. So what would be the total number of valence electrons here in C6H6? We have 6 times 4, so 24, and plus 6. So we would be having 30 valence electrons in total. So with that we can write a structure like this. Each carbon atom is having 3 sigma bonds plus 1 pi bond. Either you can write the structure like this or you can write the structure like this. In either way, each carbon atom is going to have 3 sigma bonds because we do have a hydrogen here, which we normally don't write in bond line notation, isn't it? So we do have 3 sigma bonds for each carbon and 1 pi bond. So because we have 3 sigma bonds, the steric number in benzene for each carbon is 3. Therefore the hybridization is sp2. So which means the correct answer for this is 3. In case if you are accounting for 30 valence electrons in benzene, keep it in mind that benzene has 6 CH bonds that requires 12 valence electrons. It also has 6 carbon-carbon sigma bonds that requires another 12 valence electrons, and then we have 3 pi bonds that requires 6 valence electrons. So therefore 12 plus 12 plus 6. So we can get 30. So we have utilized all the 30 valence electrons. In 3,3 dimethyl hex 1 4-ine, how many sp3, sp2 and sp hybridized carbon atoms are there? Let us draw the structure first. The root word is hex here. That means the parent chain has 6 carbon atoms. So 1, 2, 3, 4, 5, 6. At position 3 we have 2 methyl groups. Therefore CH3, CH3. At position 1 we have a carbon-carbon double bond. At position 4 we have a triple bond. Let's fill hydrogen at remaining positions so that we can satisfy the valency of carbon. Now let's figure out the hybridization. At position 1 it is sp2 because we have a double bond. Position 2 also it is sp2. Position 3 it is sp3 because we have 4 carbon-carbon single bonds. Even for the methyl groups it is sp3 because we have 4 single bonds, 3 carbon hydrogen bonds and 1 carbon-carbon bond. So therefore for the methyl groups also it is sp3. Position 4 as well as 5, because of the triple bond the hybridization is sp, and then at position 6 it is sp3 once again. So how many sp3 are there? 1, 2, 3, 4. They said carbon atoms, and therefore we have to include the methyl groups also. So that means we have 4 sp3, and then how about sp2? We have 2 sp2 carbons and we have 2 sp carbons. This means option 2 is the correct choice here. Total number of sigma and pi bonds respectively present in hex 1 4-ine are how many? The root word here is hex. Therefore we have a 6 carbon chain. Let's draw the 6 carbon chain first. 1, 2, 3, 4, 5, 6. We have a double bond at 1 position, triple bond at 4 position. Let's fill the hydrogens to satisfy the valency of carbon. We have 3 hydrogens here. We have 2 hydrogens here. We have 1 hydrogen at 2 position, 2 hydrogens at 1 position. Therefore, we have 8 CH bonds. They are all sigma, and it is a 6 carbon open chain. Therefore, it must have 5 carbon-carbon single bonds. They are sigma. Therefore, the total number of sigma bonds are 13. And then we have 1 pi bond here, and we have a triple bond here that will have 2 pi bonds. Therefore, we should have 3 pi bonds. Therefore, 13 and 3. Option 1 is correct. The number of non-polar molecules from the following is how many? To decide whether a molecule is polar or non-polar, we need to know the dipole moment of a molecule. So therefore, polarity depends on dipole moment. If the dipole moment is 0, then we can say the molecule is non-polar. On the contrary, if the dipole moment is non-zero, then we can say the molecule is polar. So now, in general, the homonuclear diatomic molecules will have 0 dipole moment. So for example, this is homonuclear diatomic molecule H2. For H2, the dipole moment will be 0. So therefore, we can count that. On the contrary, heteronuclear diatomic molecules such as HF, HCl, for these ones, the dipole will be non-zero. Why? Because of the electronegativity differences.
So basically in HF the dipole orientation will be this way because fluorine is more electronegative than hydrogen. Likewise for in HCl2 the dipole moment orientation will be this way. And in polyatomic molecules, if the dipole moment is 0, it is mostly due to symmetry. So for example, in CO2, we do have polar bonds. However, they cancel each other. One is in this direction, but another is in the opposite direction. And therefore, the dipole moment will become 0 in CO2. So this means we can count this one also. In H2O and SO2, they are not linear molecules. So therefore, we will have dipole moments in those molecules. In H2O, this is the molecule. So there will be a net dipole in this case, in this direction. So therefore, the dipole moment for water is non-zero. Likewise for SO2 also, because SO2 is slightly bent because of lone pair bond pair repulsion. So therefore, we will have dipole moment for this molecule too. So here also the dipole moment will be non-zero. So we can't count those. How about CH4? In methane, because of symmetry, because it is tetrahedral, because of symmetry, the dipole moment will be 0. Therefore, we can count methane. NH3, the dipole moment will be non-zero, so we can't count that. Like methane, the hybridization of the central atom in ammonia is sp3. However, the dipole moment is still non-zero in this case. Even though the hybridization is same, just like methane, when it comes to dipole moment, it becomes non-zero because we have a lone pair of electron whose dipole orientation would be in this way. And also, the molecular geometry of ammonia is trigonal pyramidal, not tetrahedral. So therefore, the dipole moment is non-zero for ammonia. For trichloromethane, the hybridization of the central carbon atom is sp3 and the geometry is tetrahedral, just like methane. However, the dipole moment will be non-zero in this case because we have two different kinds of bonds. One is the CH bond and another is the CCl bond, and therefore the net dipole moment will be non-zero. If it is CCl4 tetrachloromethane, then the dipole moment will be 0. But we don't have CCl4. We have CHCl3 trichloromethane. Therefore, for trichloromethane, the dipole moment is non-zero and we shouldn't count that. BF3, once again because of symmetry, the dipole moment will be 0. Fluorine is more electronegative than boron. But still because of the symmetry of the molecule, the dipole moment will be 0. So this means that we have 4 molecules where the dipole moment is 0. Therefore, the correct answer is 4 here. In the Lewis dot structure for NO2 minus, that is nitrite ion, what is the total number of valence electrons around nitrogen atom is? For questions like this, we first need to find out the best Lewis structure possible and then we can count the total number of valence electrons. But to write the Lewis structure, first of all, we need the total number of valence electrons in the molecule itself. Atomic number of nitrogen is 7 and therefore the electronic configuration is 1s2, 2s2, 2p3. We have 5 valence electrons in nitrogen and then atomic number of oxygen is 8 and therefore the electronic configuration is 1s2, 2s2, 2p4. We have 6 valence electrons but we have 2 oxygen atoms. So therefore we have 12 valence electrons and then for the negative charge we have to count 1 valence electron. So therefore 1 here. So in total we have 18 valence electrons. So with the 18 valence electrons, let us first write the best Lewis structure. Compared to oxygen, electronegativity of nitrogen is less. Therefore, let's put the nitrogen atom at the center and 2 oxygen atoms on either side. Let's put 1 bond pair. between nitrogen and oxygen, and then let's put 3 lone pairs around each oxygen atom. If we do that, then we would be accounting for 16 valence electrons in total, but we still have 2 more valence electrons. Let us put that as a lone pair on top of nitrogen. If we do that, then the oxygen atom satisfies the octet configuration, but the nitrogen atom doesn't. Around nitrogen, we have only 6 valence electrons. Is this the best Lewis structure? No, it is not. In the best Lewis structure, all the atoms should have 8 electrons around it, because both the atoms here are from period 2. So therefore, let's send one lone pair to the bond pair. If we do that, then we will have octet configuration for all atoms, and based on formal charges, we can see whether this is the best Lewis structure or not. Now we have 8 valence electrons around each atom. Let's determine the formal charge to see whether this is the best one or not. Formal charge is equal to total number of valence electrons in the atom minus total number of lone pairs of electrons in the molecule minus total number of bond pairs of electrons divided by 2. So if we calculate the formal charge for nitrogen, then it is 5 minus 2 minus, we have 3 bond pairs, and therefore 6 by 2. Therefore, this will be 3 minus 3, and that is equal to 0. So we have a 0 formal charge here. If we calculate for this oxygen atom, that is on the right hand side, then it would be 6 minus 6, because we have 3 lone pairs. Each lone pair has 2 electrons, and then 1 bond pair, so 2 by 2. So it would be minus 1 for this oxygen, and then if we calculate the formal charge for this oxygen atom, that is there on the left hand side, then it would be 6 minus 4 minus 4 by 2. Therefore, this will be 2 minus 2, and that is equal to 0. So we do get the net charge of minus 1 if we sum up everything, but at the same time, for nitrogen as well as one of the oxygen atoms, the formal charges are 0. Therefore, this is the best Lewis structure. Here they are asking total number of valence electrons around nitrogen atom in the best Lewis structure. Therefore, if we count the bond pairs as well as lone pairs, it would be 8. Therefore, 8 is the correct answer here.
By the way, when we write the Lewis structure for ions, whether it is a cation or anion, we usually mention the Lewis structure and then put a square bracket and then mention the net charge. That's the way we specify the Lewis structure of cations and anions, and therefore this is a better way of representing Lewis dot structure for nitrite ion. We have 4 different structures in list 1, 4 different IUPAC names in list 2. We need to match these two and figure out the correct option here. Whenever these kind of questions are given, find out something that is distinctly different. We have an alka die in here that is distinctly different. Therefore, let us figure that out first. 1, 2, 3, 4, 5. 2 methyl 1, 3 pentadiene. This means that C must match with 4. We have an alkene here. Therefore, let us find out the IUPAC name for this structure. 1, 2, 3, 4, 5. 4 methyl pent-1ene. That should be the correct IUPAC name for this structure. This means that D must match with 1. So C is matching with 4, D is matching with 1. This means that option 2 and option 4 are wrong. Let's figure out one more thing. Let's figure out B. We have a carbon, we have 2 methyl groups, and then we also have 2 propyl groups, CH2, CH2, CH3, and then on this side also propyl, H3C, CH2, CH2. Let's number it. 1, 2, 3, 4, 5, 6, 7. At 4 position, we have 2 methyl groups. We have 7 carbon atoms in the parent chain. Therefore, this must be 4, 4 dimethyl heptane. This means B must match with 3. This means option 3 is the correct choice. A must match with 2. Let's check that out. 1, 2, 3, 4, 5. We have C2H5 here. That can be considered as 6 and 7. We have an ethyl group at 3 position, methyl group at 5 position. So 3 ethyl, 5 methyl, heptane. So A is matching with 2. This means that option 3 is the correct choice here. What is the IUPAC name of the given compound is? For this question, I think they want you to find out the IUPAC name without worrying about the stereoisomerism. So we don't have to worry about RS configuration here. Even though we have 2 chiral centers, the IUPAC name written here is without worrying about that, and therefore let's not worry about the RS configuration. So we have a carboxylic acid functional group, we have an aldehyde functional group, we have an alcohol functional group, and then we have an alkene. Now we know that carboxylic acid would take the top precedence, and therefore the numbering has to start from here. 1, 2, 3, 4, 5, 6, 7. Total we have 7 carbon atoms in the parent chain, and therefore hept should be the root word which is given in all the options. Now the aldehyde as well as alcohol will become substituents, and therefore 2-formyl 4-hydroxy hept-16-oic acid should be the correct name, and therefore option A is correct. 2 compounds are given, their IUPAC names are also given, and we need to figure out whether they are correct or not and then pick the correct statement. Compound A name is given as 4-chloro-1,3 dinitrobenzene. Both halogens as well as nitro groups are substituents. So this means that the numbering is done this way: 1, 2, 3, 4. But is that correct? No, it is not correct, because we can also do the numbering on the other way around: 1, 2, 3, 4. If we number it that way, then it is 1, 2, 4 as a set. But if we number it this way, then it is 1, 3, 4 as a set, and therefore 1, 2, 4 as a set is the correct way of numbering. That means the correct name is 1-chloro 2,4 dinitrobenzene is the correct name. Therefore statement 1 is incorrect. This means option 3 is wrong, option 4 is also wrong. And then in statement 2, 4-ethyl 2-methyl aniline. We have aniline and 2 substituents. So let's do the numbering: 1, 2, 3, 4. 4-ethyl 2-methyl aniline, because we have to follow the alphabetical order. So this means that this compound name is correct. Therefore option 2 is correct. Statement 1 is incorrect, but statement 2 is correct. We see a carboxylic acid functional group. We do see an ester functional group. Between carboxylic acid and ester, we know that carboxylic acid gets higher precedence, and therefore the carboxylic acid should be treated as a functional group and the ester should be treated as a substituent. When ester becomes a substituent, the prefix is alkoxycarbonyl. In this case we have a methyl, and therefore it is methoxycarbonyl. That's the correct prefix, and the numbering has to be done this way: 1, 2, 3, 4. We should not choose the carbon atoms that are there in the substituent as part of the parent chain. They are just part of the substituent. Therefore the numbering has to be done this way. We do see a methyl group at 2 position. Therefore 3-methoxycarbonyl 2-methyl, because until here it is meth, and then what differentiates is the O and Y. So in terms of alphabetical order, methoxycarbonyl has to be referred first. Therefore 3-methoxycarbonyl 2-methyl butanoic acid, because we have 4 carbon atoms in the parent chain. Therefore option 3 is correct. Before we solve this problem, let me ask this question. Let's say you have a molecule like this. How do you name that? If you have a molecule like that, then 1, 2, 3. That's the numbering scheme you would follow, because as per the alphabetical order, ethyl should come first. Even if you number it on the other way around, choosing methyl group first, still the locants are at 1 and 3 position, and therefore the preferred choice is this one, because as per the alphabetical order we have to put the ethyl group first, and therefore this compound name is 1-ethyl 3-methyl cyclohexane. Now let's come to the actual problem. 1, 2, 3. So this means the substituents are at 1, 3, 3 if we follow this numbering scheme. On the contrary, if we follow this numbering scheme, then the substituents are at 1, 1 and 3 position. The point of difference comes here. So which one we should follow now? Obviously the one in red we should follow. That's the correct one, and the one in blue is wrong. Why? Because as per the lowest locant rule, the 113 positions, substituents having 113 is the correct way of numbering, not 133, because that gives a higher number to the substituents. But still we have to follow alphabetical order, and therefore 3-ethyl 1,1 dimethyl cyclohexane. That's the correct IUPAC name for this molecule. What is the total number of possible stereoisomers of dimethyl cyclopentane? First of all, this is not a difficult question, but at the same time, if you are not very clear about the concept of meso compounds, enantiomers, and the difference between stereoisomers and structural isomers, then there are plenty of opportunities to make a mistake on questions like this. Let me write a structural isomer for dimethyl cyclopentane. The reason I am showing this isomer is because if you are not very clear about the concept of stereoisomerism and structural isomerism, then you would be making a mistake on questions like this. So this is a structural isomer. This is not a stereoisomer, because this molecule is achiral. There is no chiral center in this molecule. Therefore, this shouldn't be included in the count at all. So let me remove this. Now we can write 1, 2 dimethyl cyclopentane with both the methyl groups up. If we do that, then we are having two chiral centers now, isn't it? This is a chiral center, this is also a chiral center. So therefore 2 to the power n, we expect 4 isomers. But are we gonna get 4 isomers? No, because this is a meso compound. The molecule has a plane of symmetry. Half of the molecule is a mirror image to the other half. So what will happen when we have mesomer? We won't get the maximum isomers 4. We will get only 3 isomers, isn't it? Because one of them is a meso compound. This one as well as this one are identical. Whether you put the methyl groups, both the methyl groups up or both the methyl groups down, they are one and the same. Because you can reach to this one if you rotate the molecule 180 degree. Whether you are rotating clockwise or counterclockwise, it doesn't matter. If you rotate 180 degree along the plane of symmetry, then you can get the other one. So that means both are identical. Both are meso, both are identical. So therefore this must be counted as one isomer. This is achiral. I am just writing it. That doesn't mean that these are two isomers. This is one isomer. Okay? Because if you just rotate 180 degree, you can reach to the other one, and we can clearly superimpose both of them. Because half of the molecule is a mirror image to the other half, the net optical activity of meso compound will always be 0. And then we can also get a pair of enantiomers. If you put one methyl group up and one methyl group down, then we can get a pair of enantiomers. So let's say this methyl group is up and then this methyl group is down, and let's assume that this is our mirror plane. Then the mirror image will be like this, and these are non-superimposable mirror images. That means these are enantiomers. So therefore this must be considered as two stereoisomers, enantiomers. Likewise, we can write 1, 3 dimethyl cyclopentane with both the methyl groups up. That would once again will become a meso compound, isn't it? If both the methyl groups are up or both the methyl groups are down, they are one and the same, they are identical, and this is a meso compound once again, because once again we have a plane of symmetry. This is the plane of symmetry now. So if you rotate 180 degree, then we can get this one, but that doesn't mean that this is a different isomer. This is one and the same. These two are identical, meso achiral. Now let's put one methyl group up, one methyl group down. So number 5. So if we are writing like this, let's say one methyl group down, one methyl group up for the 1,3 case, then once again we will get a pair of enantiomers. Let's say this is our mirror plane, and then this would be the mirror image. These two are enantiomers because they are non-superimposable, therefore they are enantiomers. So therefore this must be considered as 2 isomers. So in total we can get 6 isomers. Therefore the correct answer is 6. 2 of them are achiral, 4 of them are chiral. Even though it is achiral, it should still be considered as a stereoisomer. Just because a molecule is achiral having chiral centers, it doesn't mean that it is not a stereoisomer. It is a stereoisomer. Okay, meso compounds are indeed stereoisomers. The net optical activity goes to 0 because half of the molecule is a mirror image to the other half of the molecule. The possible number of stereoisomers for 5-phenyl pent 4-in-2-ol is how many? Let us first draw the structure of this molecule. Here the root word is pent, that means the parent chain contains 5 carbon atoms. Therefore 1, 2, 3, 4, 5. At 2 position we have a alcohol functional group, and then at 4 position we have a carbon-carbon double bond, and then at 5 position we have a phenyl substituent. Let's number it 1, 2, 3, 4, 5. We have a chiral center at 2 position, therefore this could be R as well as S, but we need to consider geometrical isomerism also here. Therefore that is another stereo center. So the number of stereo centers here is equal to 2. We know that number of stereo isomers is equal to 2 to the power n, where n is the value of the number of stereo centers. Therefore this is 2 to the power 2, therefore this is 4. Therefore the correct answer is 4 here. Here the IUPAC name of the compound is given without considering stereoisomerism. But once we draw the molecule like this, let's say OH in this way and then hydrogen behind, then we need to explicitly specify the absolute configuration. How do you name this now? So we have hydrogen here, as per Kahn-Ingold-Prelog rules. If we assign the priorities, then hydrogen will get the least priority, carbon will get the most priority because the atomic number of carbon is higher than the atomic number of hydrogen. So here our least priorities are on the opposite side. Therefore this is a E isomer, isn't it? This E could be R and S, and then when we have Z isomer, then that can also have R and S. That's why the answer is 4. So now let us assign the absolute configuration at 2. The OH will get the top priority. Therefore that is 1 as per Kahn-Ingold-Prelog rules. Hydrogen will get the least priority, that is 4. Here we have a carbon that is attached to 2 hydrogens and then another carbon on the other side. Therefore this priority should be 2 here. And then here we have a carbon that is attached to 3 hydrogen atoms. Therefore this should be 3. Let us say we are looking at the molecule from here. We know that the OH is towards us and the hydrogen is behind. In this case we can put it this way: 1 here and the methyl group is at the tops, therefore 3 here, and then 4 on the right hand side, so 4 here, and then 2 here. But we cannot determine the absolute configuration this way. We need to bring the least priority group down. Therefore, let us do one swap between these two. If we do that, then 1 here, 4 here, 3 here, 2 here. Let us do another swap, because when we go clockwise or counterclockwise, the numbers has to be in a sequential manner, 1 2 3 or 3 2 1. It cannot be 1 3 2. Therefore, let's do another swap here. 1 2 3 4. Now we can go clockwise, 1 2 3. This means this is R. The original should also be R, because we have done 2 swaps. Therefore, the correct IUPAC name is 2R and then 4E, then 5 phenyl pent 4ene 2-ol. Instead of alcohol functional group towards us, if hydrogen is towards us, then this will become 2S 4E 5 phenyl pent 4ene 2-ol. Likewise, we can draw 2R4Z and 2S4Z. In that case, what we need to do is we need to put both the hydrogen atoms on the same side. What is the total number of stereoisomers of the given compound is? Number of stereoisomers depends on number of stereocenters. Chiral centers are sometimes referred as stereocenters, and we have to include geometrical isomerism also as a stereocenter. So we have 2 double bonds here. Both of them can exhibit geometrical isomerism. So therefore, stereocenters due to double bonds is 2, and also we have a chiral center here, because that carbon is connected to a methyl group, and then we have a methylene unit here, and then we have this entire unit, and then there is a hidden hydrogen, and therefore this is a chiral center. So therefore, the total number of stereocenters in this case is equal to 3. Number of stereoisomers is equal to 2 to the power n, where n is the number of stereocenters. So therefore, 2 to the power 3, and that is equal to 8. This means option B is correct. Here I have shown all the stereoisomers that are possible. So when you name it, then you can realize that we have indeed 8 stereoisomers in this molecule. So how do you name this molecule? I will just name it to 1. Maybe rest of them you can try it yourself. So this is 1, 2, 3, 4, 5, 6, 7, 8. The bromines are in 180-degree position. That means normally you call it as trans, but as per Kahn-Ingold-Prelog rules, we can go for the EZ convention. So if we go for the EZ convention, then this is an E isomer, isn't it? Because the higher priorities are on the opposite side. So therefore, at 2 position it is E. How about at 6 position? Here we have a hydrogen. Here also there is a hydrogen. So the low priorities are on the same side, or you can also say high priorities are on the same side. So therefore, at the 6th position it is Z. And then how about at 5 position? What is the absolute configuration there? So we have a chiral carbon here, and then we have carbon on this side, carbon on this side, carbon on this side, and there is a hidden hydrogen. So the hidden hydrogen obviously gets priority number 4. That gets the least priority. And then for this carbon, it is connected to hydrogen, hydrogen, hydrogen. Whereas for this carbon, it is connected to 1 carbon and 2 hydrogens. For this carbon, we can consider it as carbon connected to carbon, because we have a double bond, and then 1 hydrogen. So obviously, the top priority must be given to this, and then this one, and then this one. So if we are looking from this angle, then the Fisher projection we can write it this way. 4 is on our right hand side and then 3 is on our left hand side, 1 is top and then 2 is bottom. We can't determine absolute configuration like this because we need to bring the least priority group down. So therefore bring the 4 down, do one swap between 2 and 4. So 2 goes on the right hand side and then 1 stays where it is, 3 stays where it is. This is clockwise. So this means R, but we did one swap, therefore the original is yes. Therefore at 5 position the absolute configuration is yes. So therefore the IUPAC name for this molecule is 5S. When you have geometrical isomerism as well as chiral center, you need to specify the absolute configuration first. You shouldn't start like 2E and then 5S. 5S should be mentioned first and then 2E and then 6Z and then 2, 3 dibromo and then 5 methyl oct or octa because we have a diene. So octa 2, 6 diene. That's the correct IUPAC name for this molecule. What is the total number of structural isomers possible for the substituted benzene derivatives with the molecular formula C9H12 is? Let us first determine the degree of unsaturation for C9H12. Therefore, this is a hydrocarbon. So, for a hydrocarbon it is 1 plus number of carbon atoms minus number of hydrogen atoms by 2. So, therefore, this is equal to 1 plus 9 minus 12 by 2 and that is equal to 10 minus 6 and that is equal to 4. Since they said substituted benzene derivatives, so let us write the benzene derivatives. Benzene has a ring and 3 double bonds. So, together it accounts for 4. Let us put a propyl group, that would become one isomer because this is C6H5 plus C3H7. So, together it becomes C9H12. We can also write another isomer, that is putting a isopropyl group. So, that is isomer 2 and then let us put a ethyl group and a methyl group. So, that is one isomer. Let us shift the position of the methyl group. So, instead of putting it at second place, let us put the methyl group at third place. So, 1 3 and then we can also put 1 4, that is this one. So, we got 5 isomers. So, we are exhausted with the ethyl methyl combination. Therefore, let us put 3 methyl groups now. So, 1 2 3, that is one isomer. Let us shift the position of one methyl group, keep 2 of them as such. So, this is another isomer. We can also write another isomer, that is 1 3 5 1 3 5. We are exhausted with all the options. Any other combinations we put, it would become a repetition and therefore we got 8 isomers. That means the total number of structural isomers possible for the substituted benzene derivatives with the molecular formula C9H12 is 8. The number of optical isomers in the following compound is how many? Number of optical isomers is equal to 2 to the power n, where n is the number of stereocenters. In this case, chiral centers and stereocenters are one and the same and therefore we need to figure out the number of chiral centers here. When we call something as a chiral center, if a carbon atom or heteroatom is attached to 4 different groups, either a carbon or a heteroatom is attached to 4 different groups, then we can say that it is a chiral center. In this case, we are just going to have chiral carbons and therefore let us figure out the chiral carbons. Instead of figuring out the chiral carbons, let us eliminate those that are not chiral carbons. We can eliminate the sp3 carbons that are methyl groups. We can also eliminate the sp3 carbons that are methylene groups. So, both methyl as well as methylene groups we can eliminate because here we have 3 hydrogens. So, it would be 2 different groups. Here we have 2 hydrogens.
So even if it is attached to 2 different units, it will be 3 different groups, and therefore these things we can eliminate. So methyl group here, let's eliminate that. CH2 here, CH2, 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 these are all CH2. So we eliminated all those things, and now let us round those carbons that are remaining. 1, 2, 3, 4, 5. These could potentially be chiral centers. Let us check these one by one. We have a hidden hydrogen here, methyl group, CH2 on this side, CH here. Therefore, this is indeed attached to 4 different units. How about here? We have a hidden hydrogen here. We have CH on this side, CH2 here, CH here too, but this CH is different from this CH because this CH is connected to methyl group, whereas this one is methylene and methylene, and therefore this is indeed chiral. How about here? We have hidden hydrogen once again, CH on this side, CH2 on this side, CH2 on this side. But going on this side is different from going on this side. Let us look at the second carbon, CH2, CH2. But here if we go on this side, it is CH2 and then CH, and therefore there is asymmetry is there. This means this is indeed chiral. How about here? Once again, hidden hydrogen, and then we have a tertiary carbon here, and then CH2 here, CH2 here. Same logic. Going on this side is different from going on this side. Therefore, this is indeed chiral. Look at the second carbon, CH2, CH2, but here CH2, CH. Therefore, there is asymmetry. Here we have bromine here, CH2 on this side, CH2 on this side, and CH on this side. Look at the second carbon, CH2, CH2. Here it is CH2 and then CH. Therefore, there is asymmetry. This means that we have 5 chiral carbons. So 2 to the power 5. 2 to the power 4 is 16. So 2 to the power 5 is 32. This means 32 is the correct answer here. In list 1, 4 different isomers are mentioned, and in list 2, pairs of 4 different sets of compounds are given. We need to match these two and find out the correct option. What is isopentane? 2-methyl-butane is isopentane. Molecular formula is C5H12. This is 2-methyl-butane, that is referred as isopentane. What is neopentane? 2,2-dimethyl-propane is referred as neopentane in the old literature. 2,2-dimethyl-propane. The parent chain length is different. One is butane, another is propane. So therefore, these two are chain isomers. Therefore, one should match with the Q. So this means 3 is wrong, 4 is also wrong. How about the next one? Propanol. Propanol is CH3, CH2 and then aldehyde. Molecular formula is C3H6O. Propanone, that is CH3, C double bond O, CH3. So we have an aldehyde in one case, we have a ketone in the other case. Therefore, these two are functional isomers. This means 2 should match with a R. So therefore, option 1 should be correct. For the sake of completeness, let's check the other two also. Methoxypropane, and that is CH3O and then CH2, CH2, CH3. That is methoxypropane. And then ethoxyethane, that is CH3, CH2O and then CH2, CH3. We have different alkyl groups, and therefore these two are metamers. Molecular formula in this case is C4H10O, and then for 4 it is given as N-propanol and isopropanol. N-propanol is CH3, CH2, CH2OH, that is N-propanol, and then isopropanol is CH3, CHOH and then CH3. Molecular formula is C3H8O in both the cases, and these two are position isomers.
because they differ by the position of the alcohol functional group, and therefore 4 should match with the yes. Therefore option 1 is the correct choice here. Thyroxine, the hormone, has the following structure. What is the percentage of iodine in thyroxine is? We need to find out the nearest integer. In this case, percentage of iodine is equal to total weight of iodine divided by total weight of the compound times 100. First of all, we need to figure out the molecular formula of the compound so that we can find out the molar mass of the compound. So, benzene ring has 6 carbons. We have 2 benzene rings. So, C12 and then 13, 14, 15. So, we have 15 carbon atoms. We have how many hydrogen atoms? We have 1 here, and then 2, and then 3, 4, 5. We have 2 hydrogen atoms here, 7. We have 2 hydrogen atoms here, 9. There is 1 more hydrogen atom here, 10. There is 1 hydrogen atom here. So 11. We have 11 hydrogen atoms. We have 4 oxygen atoms. We have 1 nitrogen atom, and we have 4 iodine atoms. So that is the molecular formula. Let's figure out the molar mass. Therefore, 15 times 12, that is 180. And then next, hydrogen, we have 11 of them. So 11 times 1, 11. And then oxygen, we have 4 of them times 16, and that is equal to 64. And then nitrogen, there is 1 nitrogen, so 1 times 14, so therefore 14. And then iodine, we have 4 of them, 4 times 127, and that is equal to 508. So therefore this total is 8 plus 4 12, 12 plus 4 16, plus 1 17, remaining 1. So 8 plus 1 9, 9 plus 1 10, and plus 7, so 17. Once again remaining 1. So we have 5 plus 2, so 777. That's the molecular weight. So therefore molecular weight is 777. Therefore percentage of iodine is equal to 508 divided by 777 times 100. To make the math easier, I am writing it as 500 divided by 750 times 100. So which is like 2 by 3. So 2 by 3 is 66.66. So since I have reduced the denominator more, I am taking it as 65. So 65% is the correct answer. So therefore 65%. So if you calculate the exact value for this, you will get somewhere around 65.37. So 65 is the nearest integer. Therefore 65% is the correct answer for this. An organic compound weighing 500 milligram produced 220 milligram of CO2 on complete combustion. What is the percentage composition of carbon in the compound is? We have to find out the nearest integer. We know that mass percent or percentage composition of an element is equal to mass of element in 1 mole divided by molar mass of the compound times 100. And therefore, what is the mass of element in 1 mole for carbon? Molar mass of CO2 is 44 gram per mole, isn't it? Because it is 12 plus 2 times 16. So that is the molar mass of CO2. So in 44 gram per mole, how much carbon is there? 12 gram. So 12 by 44. Therefore this means here we have to multiply this with 220 milligram. So that's our mass of element in 1 mole. So therefore this is equal to 12 by 44 times 220 milligram divided by molar mass of the whole compound, that is 500 milligram times 100 milligram we can cancel, 20 we can cancel, this is 1 times 5, this is 4 times 5 will be 20, so 4 remaining 2, so 20 once again, so once again 4 times 5, so 44 we can cancel, therefore this is 12%, therefore 12 is the correct answer here. Uracil is a base present in RNA with the following structure. Percentage of nitrogen in uracil is how much? Percentage of nitrogen by mass is equal to total mass of nitrogen in the molecule divided by molar mass of the molecule times 100, because it is percentage composition. Now we need to find out the molar mass. We have how many carbons? 1, 2, 3, 4. 4 carbons are there. So let's find the molecular formula first, C4, and then 4 hydrogens are there, because 1, 2, and then 3, 4, and then 2 nitrogens are there, 2 oxygen atoms are there. So therefore 4 times 12, that is equal to 48, that's for carbon, and then for hydrogen 4 times 1, that is equal to 4, and then for nitrogen 2 times 14, that is equal to 28, and then for oxygen 2 times 16, that is equal to 32. So 10 plus 4, 14, 14 plus 8, 22, remaining 2, 2 plus 4, 6, 8, 8 plus 3, 11. So 112. This means percentage of nitrogen is equal to total mass of nitrogen. We have 2 nitrogen atoms, so therefore 28 divided by 112 times 100. So this will be 4 times 7, and then this will be 1 times 7 remaining 4, so 42, so 6 times 7. So basically this is 1 by 4. 1 by 4 means 0.25. So 0.25 times 100, that is equal to 25%. Therefore 25 is the correct answer. Hello everyone, here is a question based on carbocation stability. Which among the following halides will generate the most stable carbocation in nucleophilic substitution reaction? A carbocation stability is based on combination of factors. It could be hyperconjugation, or it could be resonance, or it could be positive inductive effect, or it could be positive mesomeric effect. But in this case, we need to worry about only hyperconjugation and resonance. Bromine is the leaving group in all the cases. So in presence of a polar protic solvents, once the bromine atom is left after a heterolytic cleavage, in the case of 1, we will get a allylic carbocation, which is primary, has 1 alpha hydrogen, and it is allylic. We have a alpha hydrogen here. In the case of 2, we will get a primary carbocation once again, but it is benzylic. Therefore, it is more stable than allylic carbocation. Primary, no alpha hydrogens, but benzylic. Charge distribution will be much stronger in this case. In the case of 3, we will get a secondary carbocation. It is allylic once again, but it is secondary with 3 alpha hydrogens. We have 1 alpha hydrogen here, we have 2 alpha hydrogens here. Therefore, compared to 1, 3 will be more stable. So it is allylic. In the case of 4, we will get a tertiary carbocation, but we have 3 phenyl rings. It is benzylic, but with 3 phenyl rings, this will be much more stable than all other carbocations. So tertiary carbocation, no alpha hydrogens, but it is much more stable because of the resonance effect. Therefore, in terms of carbocation stability order, if we have to arrange it, then 4 first because it is benzylic, and then 2 benzylic once again, and then 3, and then 1. This means that option 4 is correct. That will generate the most stable carbocation. The one giving maximum number of isomeric alkenes on dehydrohalogenation reaction is which one? We need to exclude all the rearrangements that are happening. When we have alkyl halides, if we heat alkyl halides in presence of alcoholic potassium hydroxide or sodium hydroxide, we will get an alkene. So here we need to see which alkyl halide will give the maximum number of alkenes. In number 1 we have 1 bromo 2 methyl butane. So this is butane, and then 1 bromo at 2 position 1 methyl group. And dehydrohalogenation reactions are sometimes called beta elimination reactions, because at the beta position we need to have a hydrogen atom so that the dehydrohalogenation reaction can occur. So here we have 1 beta hydrogen, and therefore in presence of alcoholic potassium hydroxide and heat, what will happen is we will get 2 methyl but 1ene and also KBr and water. In 2 we have 2 bromo propane. So this is propane, 1 bromo substituent at 2 position, and when we heat this molecule in presence of alcoholic KOH, then we will get only one product, that is propene. Number 3 we have 2 bromo pentane. Let's draw the pentane chain first, 1 2 3 4 5, and then at 2 position the bromo substituent. If we are heating this with alcoholic potassium hydroxide, then we would get 3 products, because we have beta hydrogens at 2 different places. We have 3 beta hydrogens at position 1, and then we have 2 beta hydrogens at position 3, and therefore if one of the beta hydrogens get eliminated at position 1, then we would get pent-1ene. But if the dehydrohalogenation happens by utilizing the beta hydrogens at position 3, then we would get 2 products, because pent-2ene is what we will get, but pent-2ene can exhibit geometrical isomerism. Therefore it will be in 2 forms. One is the trans form and another is the cis form, or if you would like to call it E and Z, that is completely fine. But this will be the major products as per the Zaitsev rule. As per this rule, the most substituted double bond is the major product, and therefore pent-2enes will be the major product and pent-1ene will be the minor product. So we have 3 isomeric alkenes in option 3, and then 4 we have 2 bromo 3, 3 dimethyl pentane. Let's draw the pentane chain first, 1 2 3 4 5, 2 methyl groups at position 3 and 1 bromo substituent at position 2. So we have no beta hydrogens here, we have beta hydrogens only here, and this means we would get only one product here, and that is 3, 3 dimethyl pent-1ene. When we heat with the alcoholic KOH, this is the only product that we can get. So this means that option 3 is the correct choice here. The molecular formula of second homologue in the homologous series of monocarboxylic acids is which one? Carboxylic acids will have the functional group C double bond O OH. The simplest carboxylic acid that we can write is formic acid, H C double bond O OH. Here they are asking second homologue in the homologous series, and therefore the second one is acetic acid, that is CH3 C double bond O OH, and for that the molecular formula is C2 H4 O2. which means option B is correct. Hello everyone, here's a question from basic calculations in chemistry. What is the degree of unsaturation for an hydrocarbon X with a molar mass 80 gram per mole that contains 90% carbon? It is mentioned as hydrocarbon. That means that the only other element that is possible is hydrogen. We have 90% carbon here. This means we should have 10% hydrogen. Molar mass is given as 80 gram per mole, and therefore the mass of carbon is equal to 80 times 90 by 100, because it's a 90%. 90% means 90 by 100. Therefore, this is equal to 9 times 8 is 72. So, this is 72 gram. So, in 72 grams, if we want to find the number of carbon atoms, we have to divide by atomic mass of carbon, that is 12. Therefore, this is equal to 6. And then the mass of hydrogen is equal to 80 times 10 by 100, because it is only 10% hydrogen. Therefore, this is simply 8 gram. Therefore, the number of hydrogen atoms is equal to 8 by 1, that is equal to 8. Therefore, the molecular formula is C6H8. Degree of unsaturation for C6H8 is equal to 1 plus number of carbon atoms minus number of hydrogen atoms by 2. Therefore, this is equal to 1 plus 6 minus 8 by 2. Therefore, this is 7 minus 4. Therefore, the degree of unsaturation is equal to 3. Therefore, 3 is the correct answer here. Let's verify the degree of unsaturation for C6H8, whether it is 3 or not, by writing some structures. We can write a structure like this: 1, 2, 3, 4, 5, 6, one double bond, another double bond, another double bond. So, here we have 3 carbon carbon double bonds, or we can also write a structure like this: cyclic ring, one double bond, another double bond. This is also an isomer of C6H8. So, here for 2 carbon carbon double bonds 2 and then one ring, therefore, this is 3. Or we can also write a structure like this: 1 triple bond, 1, 2, 3, 4, 5, 6 and then one double bond. For triple bond, carbon carbon triple bond, it is 2, and then for 1 carbon carbon double bond 1. So, this is 3. Therefore, the degree of unsaturation value that we calculated for C6H8 is correct. The alkane from below having 2 secondary hydrogens is which one? What they mean by secondary hydrogens is those hydrogens that are connected to a secondary carbon. For example, let us take a simple case like propane. Here this carbon atom is secondary, this carbon atom is primary, and this carbon atom is also primary. These 2 hydrogens we can consider as secondary hydrogen. Now, why this carbon atom is secondary is because it is directly connected to 2 other carbon atoms, whereas the end carbons are directly connected to only 1 carbon atom, and that is why the end carbons are primary and the middle one is secondary. So, let us just write down the structures and then see how many secondary carbon atoms are there in the first place, then we have to multiply by 2. So, for 4-ethyl 2,4 dimethyl octanes, let me write the structures in bond line notation so that it would be quick. Octane first: 1, 2, 3, 4, 5, 6, 7, 8, and then at 3 position 1 methyl group, 4 position 1 methyl group, and then 1 ethyl group at 4 position. Let me number it. Now, this is a secondary carbon, this is a primary carbon, and the carbon atom here, this one is tertiary carbon, this is primary, this is primary, this is also primary, this is a quaternary carbon, the one here, and this is a secondary carbon, this is also secondary, and this one is secondary, this is also secondary, this is primary. So we have how many secondary carbon atoms? We have 5 secondary carbon atoms in this case. That means we have 10 secondary hydrogens because we had 5 secondary carbon atoms. Therefore, in all those places we have 2 hydrogens. Therefore, this is not the correct answer. Now, number 2, we have 2244 tetramethylhexane. So, let us write the hexane first. 1, 2, 3, 4, 5, 6. At 2 position, 2 methyl groups. 4 position, 2 methyl groups. Let's number it. And then, so this is primary, primary, primary. This is quaternary. This one is secondary. And then this is quaternary carbon again. This is primary, this is primary, this is secondary, and this one is primary. So we have 2 secondary carbon atoms, and that means we have 4 secondary hydrogens. Therefore, this is also not the correct answer. Number 3, we have 2233 tetramethylpentane. So 1, 2, 3, 4, 5, 2 position, 2 methyl groups, 3 position, 2 methyl groups. Let's number it. We have primary carbon here, here as well as here. We have quaternary carbon here, quaternary carbon here, primary, primary. This position is secondary and this is primary. So we have only 1 secondary carbon. That means we have 2 secondary hydrogens here. Therefore, this is the correct answer. Let us work it out for number 4 also. We have heptane, tetramethylheptane, 1, 2, 3, 4, 5, 6, 7, and 2 position, 2 methyl groups, 4 position, another methyl group, 5 position, another methyl group. Let's number it. Primary, primary, primary. This is quaternary carbon. This is secondary. This is tertiary. This is primary. This is primary. This one is tertiary. This is secondary. And this is primary. We have 2 secondary carbon atoms. That means we have 4 secondary hydrogens. Therefore, option 3 is the correct choice here. The correct order for acidity of the following hydroxyl compounds is which one? We have methanol, tertiary butyl alcohol, and then phenol, and then para-methoxyphenol and para-nitrophenol. Now, in these 3 cases, resonance effect will be operative because we have the phenyl ring, whereas in these 2 cases, CH3 is there and therefore positive inductive effect will be operative. And we also know that NO2 is a strong electron withdrawing group, whereas methoxy is a electron donating group. So therefore, when we have NO2, this will have negative mesomeric effect. So which means it can pull the electrons away, isn't it? And we also know that when we talk about acidity, we have to see the stability of the corresponding conjugate bases, how stable the conjugate base is. Depending upon that, the acidity of the molecule will be. So obviously, once the proton leaves, we will have methoxide in the case of A, and we will have tertiary butoxide in the case of B. Now, between these two, which one will be more stable? Obviously, methoxide will be more stable. Why? Because it is smaller. So therefore, this can be easily solvated. More water molecules can surround this. Whereas tertiary butoxide ion is a bulky one, and therefore during solvation the water molecule cannot effectively surround this one. So this means that it will be less stable. Even though inductive effect is there in both the cases, it is the solvation that would decide, and plus the steric hindrance. So therefore, if we are talking about the stability order of conjugate bases, then tertiary butoxide ion will be less stable compared to methoxide ion, which means methanol will be more acidic than tertiary butyl alcohol. This means A has to be greater than B. So therefore 3 is definitely wrong, 4 is also wrong. And when it comes to phenol and phenol derivatives, because electron donating group is there, the corresponding conjugate base will be less stable, because if we want to increase the acidity, we basically have to pull the electrons away, whereas in this case we have lone pair here. So that means that can donate the electron, that is not pulling away the electrons that are here once the proton is left. So which means that the next one should be D. I am talking about the stability order of the conjugate base, and then C, the phenoxide ion, and then E. So we have to see in the reverse way now. So E will be more acidic, obviously, because NO2 is a strong electron withdrawing group. We will have negative mesomeric effect. In these two cases we will have positive mesomeric effect. So which means that option 1 is correct, because E will be more acidic than phenol, and which will be more acidic than para-methoxyphenol. And then we already figured out that A is more acidic than B. So this means option 1 is correct. Which of the following are aromatic? If a compound has to be aromatic, it has to be planar and continuous delocalization of pi electrons should be there, and it has to obey the 4n plus 2 pi electrons rule, that is the Huckel's rule. Here n value runs from 0. In structure A, we do see sp3 hybridized carbon atoms. That means continuous delocalization of pi electrons are not there. In total, it has 8 pi electrons. So it is not going to obey the 4n plus 2 pi electron rule. It is not going to have continuous delocalization of pi electrons, and because these two carbons are sp3 hybridized, the structure won't be planar. Therefore you can call this as non-aromatic. So this means option 2 is wrong, option 3 is also wrong. For structure B, we should see only this, we shouldn't see the entire thing. Okay, we should see only the ring structure. So in the ring structure we have 6 pi electrons. So it is obeying the 4n plus 2 pi electron rule. Delocalization of pi electrons are there in the ring and it is planar. Therefore B is definitely aromatic. When it comes to C, it has 10 pi electrons. Delocalization of pi electrons are there. It is obeying Huckel's rule. But the question is it planar? This molecule is not planar, because these two hydrogen atoms will repel each other. The hydrogens in the 1 and 6 positions will interfere with each other and force the molecule to be out of plane. Therefore, this molecule is not planar, even though it is having delocalization of pi electrons and it is obeying Huckel's rule, it is still not aromatic because it is not planar. Therefore, you can say this as non-aromatic. How about option D? In option D, we have 14 pi electrons. The molecule is indeed planar, delocalization of pi electrons are there, and therefore this is aromatic. It does obey the Huckel rule with the n value equal to 3. Therefore, B is aromatic, D is aromatic. This means that option 1 is correct.